Jet propulsion can be defined as the force which is generated in the opposite direction to that of a discharge of fluid under pressure escaping through an opening. The force that makes a lawn sprinkler, similar to the one shown here, rotate when water flows through it, is one example of jet propulsion that is readily apparent in everyday life. And the thrust that sends rockets, like this one, into space is another, which is perhaps not such an everyday occurrence. Whatever the form that the device utilizing jet propulsion takes, it is essentially a reaction engine, which operates on the principle of the third law of motion, as stated by the English physicist Sir Isaac Newton in 1687, which is that every action has an equal and opposite reaction. The first recorded use of a reaction engine was by Hero of Alexandria in 250 BC. Hero's engine, a representation of which is shown here, consisted of a sphere into which steam was introduced under pressure. The steam was fed through apertures in the centre of the bearings, upon which the sphere was allowed to rotate. Allowing the steam to escape through nozzles in two bent tubes mounted opposite one another on the surface of the sphere created thrust, which caused the sphere to rotate around its axis. It is alleged that Hero invented his engine while he was investigating different methods of opening the doors of a temple in Alexandria. In recent times, one of the first attempts at creating jet-powered aircraft resulted in the development of a hybrid design. An Italian, Secondo Campini, designed a system whereby an external power source, in this case a conventional piston engine, powered a compressor. The output of the compressor was mixed with fuel. The mixture of air and fuel ignited and jet thrust resulted. Campini collaborated with the Italian aircraft manufacturers Caproni, and in August of 1940 the Campini-Caproni CC-2 flew. Although the Italians were unaware of it, a year earlier than this the Germans had flown their version of a jet aircraft, the Heinkel 178. This aircraft was powered by an engine designed by a young German scientist called Hans von Ohain. Despite its relatively sparkling performance for the era, it could travel at speeds in excess of 400 miles per hour. The German Air Force initially paid it scant regard, and it was never produced in any quantity. On the 8th of April 1941, the first official flight of the Gloster E-2839 aircraft took place at Brockworth in Gloucestershire. Sir Frank Whittle had submitted patents for his jet engine in 1930, but it was not until 1939 that sufficient financial and technical backing was found to enable him to manufacture a flyable version of his engine. The firm of Rover had reluctantly initially been contacted to produce the Whittle engine, but Rolls-Royce, who could see its potential, eventually took over development of the engine, one of which is shown here. Rolls-Royce reworked the Whittle design to produce the Derwent engine, an example of which is depicted here. This engine was capable, in its Mark IV version, of producing 2,450 pounds of thrust. Later versions of the engine, capable of 3,600 pounds of thrust, were used to power the Gloster Meteor F8, like the one shown here flying at an open day at Royal Air Force Kemble in the year 2000. During a visit to the United States in early 1944, the leader of the Rolls-Royce design team found that General Electric were developing engines capable of producing up to 4,000 pounds of thrust. As a response to this, after his return, he initiated a project which culminated in the Nene engine, which at the time was the most powerful engine in the world, with 5,000 pounds of thrust. Possibly one of the most important but least publicised uses of this engine was its incorporation into the Russian MiG-15 aircraft, which was so effective in the Korean conflict. One critical difference between the German engines used in the Heinkel and the later Messerschmitt 262 and those developed from Sir Frank Whittle's original engine was the type of compressor employed. While the Whittle engine used a centrifugal compressor similar to the example shown here, the German engines, like the BMW 003 model used in the Heinkel 162, utilised an axial flow compressor, similar in design to the cutaway model shown. Axial flow compressors have several advantages over the centrifugal compressor. For instance, whereas the centrifugal compressor compression ratio is limited to approximately 12:1 when the maximum of 2 stages are used in series, by adding more stages to an axial flow compressor, compression ratios as great as 40:1 can be obtained. The term compression ratio refers to the ratio of the pressure at the outlet of a compressor to that at its inlet. A second advantage of the axial flow compressor, almost as important as the first, is that the mass flow which can be obtained through an axial flow compressor is potentially much greater than the mass flow which can be achieved through a centrifugal compressor. As a consequence of these factors, the development of the early centrifugal compressor engines was subjugated in favour of the advancement of the axial flow compressor engines, which continues today. The principle of the gas turbine engine is basically the same as that of the piston engine propeller combination. They both propel a mass of air backwards. Mass times acceleration equals force. In a gas turbine engine, the mass, m, mentioned in the equation, is the air delivered by the compressor. The acceleration in the equation is the difference in the outlet velocity of the air, VO, to that of its inlet velocity, V1, due to the addition of heat energy. Force equals m times VO minus V1, which equals thrust. With the piston engine propeller combination, the propeller drives a relatively large mass of air backwards fairly slowly, while the gas turbine throws a small mass of air backwards relatively quickly. Newton's third law states, "For every force acting on a body, there is an equal and opposite reaction." In the two cases quoted earlier, the piston engine propeller combination and the gas turbine engine, the force created by the mass of air being thrown backwards and its velocity, generates a reaction in the opposite direction, driving the aircraft forward. It must be remembered that the jet reaction does not result from the pressure of the jet on the atmosphere. In all instances, the resultant reaction or thrust exerted on the engine is proportional to the mass or weight of the air expelled by the engine and the velocity change imparted to it. The working cycle of the gas turbine engine is called the Brayton cycle, after George Brayton, an American mechanical engineer who invented the continuous ignition engine, which was the basis of the gas turbine engine. The Brayton cycle and the working cycle of the four-stroke piston engine, the Otto cycle, are very similar, as can be seen in this diagram. The induction, compression, combustion, and exhaust strokes of the Otto cycle are each matched by induction, compression, combustion, and exhaust stages in the Brayton cycle. One major difference, however, exists in that in the gas turbine engine, combustion, theoretically, occurs at a constant pressure, whereas in the piston engine it occurs, once again theoretically, at a constant volume. Power is developed in the turbine of the engine. Other differences between the piston engine and the gas turbine engine concern the continuous manner in which these processes occur in the gas turbine engine, as opposed to the intermittent procedure occurring in the piston engine. In the piston engine, only one of the strokes is utilised in producing power. The other three are effectively absorbing power, while in the gas turbine engine, the 3 idle strokes have been eliminated, thus allowing more time for the burning of fuel. This is just one of the reasons why the gas turbine engine has a greater power-weight ratio than the piston engine. The pressure-volume diagram shown here represents the working cycle of the gas turbine engine, the Brayton cycle, in its simplest form. Air at atmospheric pressure enters the engine at point A and is compressed along the line AB. Fuel is added in the combustion chambers, which is signified by point B, and the mixture is burnt, in theory, at a constant pressure. In fact, the reduction in pressure shown between points B and C indicates that pressure losses do actually occur in the combustion chamber. The drop in pressure is created by the need to produce the swirl and turbulence necessary for efficient combustion, and this causes a pressure drop throughout the combustion chamber length of between 3 to 6%. Notwithstanding this drop, a considerable increase in the volume of the air is generated within the combustion chamber. Between points C and D, the gas generated through combustion expands in the turbine, where mechanical power is extracted from the energy in the gas stream, and the jet pipe, where the remainder of the gas stream energy provides a propulsive jet as it is discharged. In theory, the gas stream pressure attains a value equal to atmospheric pressure before being ejected. As we previously stated, theoretically, combustion in the gas turbine engine occurs at a constant pressure. This is achieved partly through the continuous process of the Brayton cycle, and also the fact that the combustion chamber is not an enclosed space. These circumstances ensure that there are no fluctuations of pressure in the engine, as there are in the piston engine, where peak pressures greater than 1,000 pounds per square inch have to be accommodated. These high internal pressures necessitate utilising extremely strong and heavy construction in the piston engine, and also, if detonation is to be avoided, the use of high-octane fuels. In contrast, in the gas turbine engine, the use of low-octane fuels and relatively light construction methods are the rule rather than the exception. The turbojet is a heat engine. The higher the temperature attained in combustion, the greater the expansion of the gases, and hence the greater efficiency of the engine. There is, however, a limit to the amount of heat that can be released into the turbine from combustion. This limit is imposed by the materials from which we manufacture the nozzle guide vanes and the turbine blades. The Germans' inability to produce materials which could withstand the heat of the gas stream was the main problem with the early German gas turbine engines. Because of the poor materials used in the turbine assemblies, the engines would only run for between 10 to 20 hours before the turbine blades suffered meltdown and engine disintegration commenced, usually in a quite catastrophic fashion. The use of modern materials and extremely efficient cooling methods in the nozzle guide vanes and the turbine blades has enabled the use of much higher gas temperatures in the latest engines. This has resulted in the more modern engines having a higher thermal efficiency than their predecessors. Gases behave differently from the other two commonly studied states of matter, solids and liquids, so we have different methods for treating and understanding how gases behave under certain conditions. Gases, unlike solids and liquids, have neither fixed volume nor shape. They are moulded entirely by the container in which they are held. There are three variables by which we can measure gases: volume, pressure, and temperature. We'll discuss two of the so-called gas laws which are most pertinent to the operation of the internal combustion engine: Boyle's law and Charles's law. Robert Boyle was born in 1627 in Ireland. He made important contributions to physics and chemistry, but is best known for the law which was named after him concerning an ideal gas. Boyle's law states that, in a gas which is held at a constant temperature, the volume of that gas is inversely proportional to its pressure, or pressure times volume equals a constant. This holds true where P is the absolute pressure of the gas and V is the volume occupied when the pressure is P. Because of the interest in hot air balloons in the early 1800s in France, Jacques Charles and Joseph Louis Gay-Lussac made detailed measurements on how the volume of the gas was affected by its temperature. Just as Robert Boyle made efforts to keep all properties of the gas constant except for the pressure and volume, so Jacques Charles took care to keep all properties of the gas constant except for its temperature and volume. Charles's law, or Gay-Lussac's law, states that if any gas is held at a constant pressure, its volume is directly proportional to the absolute temperature, or, if stated as a formula, the volume divided by the temperature is a constant. Although both Boyle's law and Charles's law work in theory, we are unable, with existing technology, to make them work in practice. For instance, it's impossible as yet to increase the pressure of a gas without increasing its temperature because of the adiabatic heating which inevitably occurs. Remember the example which is consistently quoted of how a bicycle pump always heats up when air is pumped into a tyre. By using Boyle's and Charles's law together, we get a practical method of determining what is happening to the gases inside the gas turbine engine, where temperatures, pressure and volume are all changing constantly. With the scientists' usual lack of imagination, they have named the integrated Boyle's and Charles's law as the combined gas law. The combined gas law represents the relationship between volume, pressure and temperature. This may be shown as P1 times V1 over T1 equals P2 times V2 over T2. The three main stages when these conditions change in the gas turbine engine are during compression, combustion and expansion. During compression, work is done to increase the pressure and decrease the volume of the air. There is a corresponding rise in its temperature. Just as they do in the piston engine, higher compression ratios give higher thermal efficiency and lower specific fuel consumption. Notice that the velocity of the air as it progresses through the compressor is actually reducing. This is required so that when it gets to the combustion chambers, its speed is not such that it will extinguish the flame. During combustion, the addition of fuel to burn with the air increases the temperature, and there is a corresponding rise in its volume at an almost constant pressure. The velocity of the gas flow continues to reduce through the combustion phase, until the end of the combustion chamber, which, due to its convergent shape, initiates an increase in its value. The reason for this will soon be apparent. During expansion, when some of the energy in the gas stream is being converted to mechanical energy by the turbine, there is a decrease in both the pressure and temperature of the gas, with a corresponding increase in its volume. The changes in velocity over the expansion phase are a little more complicated than in the previous phases. The expansion phase is when the kinetic, pressure and heat energy in the gas stream are being converted into mechanical energy by the turbine to drive the compressor. The turbine is most efficient at converting the kinetic energy in the gas stream into mechanical energy. In order to do this, the nozzle guide vanes which precede each turbine rotor stage are shaped to form convergent ducts. At the nozzle guide vane stage, the pressure energy, and to a lesser extent the heat energy, are reduced by the convergent ducts and converted into kinetic energy, which, as you can see here, shows a dramatic rise. The turbine rotor following each nozzle guide vane stage reduces this kinetic energy by converting it and some of the remaining pressure and heat energy into mechanical energy. Succeeding nozzle guide vane stages will continue to convert the pressure and heat energy in the gas stream into kinetic energy, and the turbine rotor stages which follow them will convert that kinetic energy into mechanical energy. The gas stream is then directed into the exhaust nozzle, where the velocity decreases at the expense of a small rise in pressure. This decrease in velocity assists in maintaining the losses in the jet pipe due to turbulence at a minimum level. Finally, as the gas passes through the sharply convergent propelling nozzle, the duct shape causes a distinct increase of velocity, and the pressure of that stream drops to that of ambient in response to that increase. As the air passes through the engine, various adjustments must be made to its velocity and pressure. For example, throughout the compression stage, the air must be compressed, but no appreciable increase in its velocity can be easily tolerated. Another example, which we have already seen, occurs at the exhaust nozzle, where the pressure of the gas is dropped to that of ambient and a considerable increase in its velocity results. These changes in pressure and velocity are accomplished by the different shaped passages or ducts through which the air must pass before it exits the engine. The design of these ducts is extremely important because the efficiency with which the changes from kinetic energy to pressure energy and vice versa occur are reflected in the overall efficiency of the engine. In this example of the use of different duct shapes within the engine, it can be seen that the use of a divergent duct will increase the pressure of the air after it leaves the final stage of the compressor and before it enters the combustion chamber. This air, sometimes called compressor delivery air, is the highest pressure air in the engine. Using a divergent duct here gives a twofold advantage. First, an increase in pressure has been achieved with no expenditure of energy in driving the compressor. Secondly, a decrease in velocity has been contrived, which will serve to make the task of the combustion chamber in keeping the flame burning less difficult. This example, which we have already experienced, shows how a convergent duct is used to accelerate the gas as it passes through the nozzle guide vanes on its way to the turbine blades. The torque which is applied to the turbine blade is dependent, among other things, upon the rate of gas flow into it. It follows then that the faster we can make the gas flow into the turbine, the more torque we can transfer to the turbine. Logically, therefore, if we convert some of the considerable pressure energy of the gas stream into kinetic energy, it will be more efficient in imparting a turning effect upon the turbine and its shaft. When a compressor and turbine are joined on one shaft, the unit is called a spool. This diagram shows a single spool axial flow compressor turbojet engine. This type of engine was for a long time considered to be the most useful where an engine with a small frontal area was required, such as in fighter aircraft, where a high forward speed was the main criterion. There are, however, problems with the control of the smooth flow of air through the engine throughout its rotational speed range. More of this later. As it flows from the compressor, the air is fed directly into the combustion chambers and fuel is added and the resulting mixture ignited. The resultant increase in temperature will cause the substantial increase in volume which is required. The energy required to drive the compressor, approximately 50% of the energy in the gas stream, is now extracted from the stream as it passes through the turbine. The remaining energy in the gas stream acts as thrust as the gases pass to the atmosphere via the end of the jet pipe. This diagram illustrates both a centrifugal compressor turboprop engine and an axial flow compressor turboprop engine. The output from a turboprop engine is the sum of the shaft horsepower developed at the turbine and the residual jet thrust. This is called equivalent shaft horsepower, or ESHP. The major difference between the turbojet and the turboprop in how they handle the generated power is that in the turbojet, virtually all of the energy that remains after the compressor has been powered is used as thrust. Whereas in the turboprop, almost all the energy in the gas stream is converted into mechanical power to drive both the compressor and the propeller. Only a small amount of jet thrust is available from the exhaust system of a turboprop with an efficient turbine. It can fairly be described as residual thrust only. Apart from this difference, the airflow through the engines is virtually the same in either case. The compressor passes the air to the combustion chambers, where the fuel is added and the mixture is burnt, and because of the temperature rise, a substantial increase in the volume of air within the combustion chamber is obtained at a nominally constant pressure. The gas is now expanded in the turbines, where a drop in the pressure and temperature is converted into the kinetic energy, which is exchanged for the torque used to drive the compressor or compressors and the propeller through its reduction gear. The turboshaft engine can be thought of as a turboprop engine where the propeller has been replaced by a shaft. Turboshaft engines can be used to drive helicopter rotors. They can also be used in applications where a compact supply of electrical power is required, their output shaft being attached to an alternator. This is the type of engine normally used as the auxiliary power unit, APU, on most modern transport aircraft. Most, if not all, turboshaft engines incorporate a free power turbine. A free power turbine is a turbine that is not connected to any of the compressors. This frees the turbine from the constraint of having to rotate at a speed that suits the compressor, and this gives the turbine a much wider operating speed range. The single-spool turboshaft engine illustrated here has a reverse-flow combustion chamber system. This allows the engine to be much shorter, stiffer and lighter than it otherwise would, but does add the requirement for a centrifugal compressor to be used in the high pressure stage. This allows for the air to be thrown out radially in order that it can enter the combustion chamber in the correct direction. Other than this deviation, the airflow is similar to that previously described for the turbojet engine, up to the point where it leaves the first stage turbine. The first stage turbine, having converted sufficient energy from the gas stream to drive the compressor, the free power turbine converts any remaining energy to mechanical energy, which is utilised to drive whatever is attached to its shaft. The bypass ratio of an engine is defined as the ratio of the amount of air which is bypassed around the hot core of the engine to the amount of air which passes through the hot core. An engine with a bypass ratio in the region of about 1 or 2 to 1 would be considered to be a low bypass ratio engine, whereas an engine with a bypass ratio of around 5 to 1 would be considered to be a high bypass ratio engine. The engine shown in here is a twin-spool low bypass ratio engine. Airflow, as far as the end of the low-pressure compressor, is identical to that of a pure turbojet. But then the airflow splits into two. An amount, depending on the bypass ratio, will flow down the bypass duct, and the remainder continues into what is the start of the hot core of the engine, the high-pressure compressor. From the high-pressure compressor, the air follows the usual pattern through the combustion chambers and into the turbine, before it leaves the hot core and rejoins the bypass air in the mixer unit of the exhaust system. The propulsive efficiency of both the low and high bypass ratio engines is much greater than that of the pure turbojet at the speeds normally associated with jet transport aircraft. The term propulsive efficiency is explained later in this lesson. The specific fuel consumption of both the low and high bypass ratio engines is also much lower than that of the pure turbojet. The experience which was gained by manufacturing and operating the low bypass ratio type of engine proved that engines which dealt with a larger comparative air mass flow and lower jet velocities could deliver propulsive efficiencies comparable to those of turboprops, and indeed a higher propulsive efficiency than turbojets operating at normal cruising speeds. The advent of the fan-jet engine had arrived. This model of a triple-spool front-fan turbojet engine, shown here, represents probably the most successful early example of this type of engine, the Rolls-Royce RB211. The air enters the intake and passes immediately into the low-pressure compressor, more commonly called the fan. Here its pressure is raised before it splits to go either through the bypass duct or into the intermediate pressure compressor, the amount going to either depending upon the bypass ratio. The thrust of this type of engine is almost completely dependent on the relatively cold air going through the bypass duct, which has a high mass and relatively low velocity, hence its high propulsive efficiency. The air which passes through to the hot core, which consists initially of the intermediate and high pressure compressors, has a great deal of energy added in the combustion chambers, but this energy is required to drive all of the compressors, which includes the fan. In fact, it is the rearmost turbine, or the low-pressure turbine, which is responsible for driving the front fan, by extracting virtually all of the energy that remains in the gas stream. If it is efficient in doing its job, then there should be only residual thrust remaining where the hot gases emerge from the turbine. We previously explained that thrust is the product of mass times acceleration. It can be demonstrated that the same amount of thrust can be provided either by imparting a low acceleration to a large mass of air or by giving a small mass of air a large acceleration. In practice, the former is preferred, since it has been found that the losses due to turbulence are much lower and the propulsive efficiency is higher. In this graph, the levels of propulsive efficiency for several different types of gas turbine engine will be shown. The highest propulsive efficiency at low air speeds is offered by the turbo-propeller combination. However, above about 350 miles per hour, the propeller's efficiency does drop off quite rapidly due to the disturbance of the airflow at the tips of the blades. In comparison with the turboprop, the propulsive efficiency of the pure turbojet appears quite poor at the lower airspeeds. As the airspeed increases in excess of 800 miles per hour, however, the propulsive efficiency of the turbojet starts to improve beyond the capability of the turboprop engine to match it, and from then on there is no comparison, the eventual outcome being a propulsive efficiency close to 90%. Cruising speeds in the order of 800 miles per hour are at present out of the reach of most transport aircraft, and this fact means that in the mid-speed range, where most of the world's jet transport aircraft operate, there is a niche for the bypass engine, both low ratio and high ratio. The low and high bypass ratio engines, which includes the ducted fan or turbofan engine, have a propulsive efficiency which fits neatly between that of the turboprop and the pure turbojet. By dealing with comparatively larger mass airflows at lower jet velocities, the bypass engine attains a propulsive efficiency which exceeds that of both the turboprop and the pure turbojet at the speeds normally associated with jet transport aircraft. The use of larger and larger aircraft has meant that more passengers can be accommodated in each flight. Thus air travel has become less and less expensive for the individual. This concept of using large aircraft works well, as long as the aircraft themselves remain serviceable. If, however, one restricting component, such as an engine, becomes unserviceable on a large aircraft, then the expense involved in keeping 300 or 400 passengers fed, accommodated and happy becomes exorbitant. Engine manufacturers, in an attempt to minimize the financial burden imposed upon the users of their equipment in the event of its failure, have started to use modular construction methods which facilitate changing sections of an engine rather than the whole engine. This diagram shows how the engine is split into several modules. This concludes the introduction to the gas turbine engine. The combustion chamber or combustor of a gas turbine engine must contain the burning mixture of air, which is being passed from the compressor, and fuel from the fuel spray nozzles in order to generate the maximum heat release at a more or less constant pressure, so that the turbine receives a uniformly expanded, heated and accelerated stream of gas. In this lesson, we will look at how these objectives are achieved in a basic combustion chamber system as used in engines with multiple combustion chambers. We will then go on to look at the types of combustion chambers used in modern gas turbine engines. The multiple combustion chamber system has a number of individual combustion chambers positioned around the core of the engine between the compressor and turbine sections. A basic combustion chamber consists of two concentric tubes. The outer tube is known as the air casing, and the flame tube is fitted inside it. The flame tube is made up of a number of sections joined together by corrugated joints. It has secondary air holes and dilution air holes cut into it. The sealing ring at the turbine end of the combustion chamber allows for elongation of the chamber due to expansion. The chamber is fixed at the compressor end by being bolted onto it. It cannot expand in that direction. The sealing ring allows the chamber to expand into the nozzle box, which is the portion of the engine immediately preceding the turbine nozzle guide vanes, whilst maintaining a gas-tight seal between the chamber and atmosphere. Fuel is sprayed into the flame tube through the fuel spray nozzle. The two major problems that the combustion chamber has to contend with are the velocity of the air leaving the compressor and the temperature of the burning gases. We will look at each of these problems and see how they can be overcome, beginning with the velocity of the air leaving the compressor. You may recall from this graph that the air leaves the compressor at a slightly slower velocity than at which it enters the intake of the engine. Speeds of around 500 feet per second are not unusual. The flame rate of kerosene, that is, the speed at which the leading edge of a flame would travel through kerosene vapour, is approximately 30 feet per second. If burning kerosene was exposed to an airstream which was travelling at 500 feet per second, it would be extinguished immediately, rather like blowing out a candle. So, something must be done to slow down the speed of the airflow after it leaves the compressor, and before it reaches the fuel nozzle, otherwise the flame will not be sustainable. The air is slowed down by passing it through a divergent duct immediately before it enters the combustion chamber. The reduction in velocity achieved here is not enough, and further decreases must be achieved if the flame is not to blow out. The air is divided as it enters the combustion chamber into primary, secondary and tertiary airflows. This diagram shows how the primary air entering the flame tube passes through the snout before being divided to go through the perforated flare and the swirl vanes before entering the primary zone. The primary zone is a region of lower velocity recirculation positioned immediately downstream of the fuel spray nozzle. It is within this zone that stable combustion is achieved. The primary air is approximately 20% of the total airflow coming from the high-pressure compressor and into the combustion chamber. This is the air which is mixed in a ratio of approximately 15:1 by weight with the fuel and burnt. By being passed through the flare and the swirl vanes, the velocity of the primary air is reduced, which must happen if the flame is not to be extinguished, and the shape and position of the flare and swirl vanes also starts the air recirculating within the region. The remaining 80% of the output of the high-pressure compressor, air which has not been directed through the snout, goes into the space between the flame tube and the air casing. Some of this remaining air, approximately another 20% of the output of the high-pressure compressor, is allowed into the flame tube through secondary air holes. This air is called secondary air, and it reacts with the primary air to form a donut or smoke ring-shaped area of flame known as a toroidal vortex. The toroidal vortex stabilizes and anchors the flame and prevents it being moved through the flame tube, away from the fuel nozzle area. There is a limit to the maximum temperature of the gas exiting from the combustion chamber. This is determined by the materials from which the turbine nozzle guide vanes and the turbine rotor blades are manufactured. The slightest excursion above that temperature limit will mean distortion of the turbine blades and the possible disintegration of the turbine, with probably catastrophic results. Modern turbine and nozzle guide vane materials will allow a maximum gas temperature of between 1000 and 1500 degrees Celsius when it exits the combustion chamber. This, of course, will be the temperature of the gas exiting the chamber with full power selected. Lower power settings would require lower fuel flows and consequently would generate lower gas temperatures. The combustion chamber has to be capable of maintaining stable and efficient combustion over the full range of engine operating conditions. The temperature of the gases at the centre of the combustion chamber primary zone reaches about 2000 degrees Celsius. This is far too hot for the materials of the nozzle guide vanes and turbine blades, so the temperature of the gases must be reduced before they can be allowed to exit the combustion chamber. You will recall that 20% of the air from the compressor is used as primary air, and a further 20% as secondary air. The remaining 60% is progressively introduced into the flame tube through the corrugated joints and dilution air holes. This air is called tertiary air, and it cools the gases to a safe level for the nozzle guide vanes. Tertiary air is also used to cool the air casing of the combustion chamber. It is necessary to ignite the fuel-air mixture on engine start. This is achieved using electrical spark igniters. Because combustion is a continuous process, the igniters are switched off once the engine has started satisfactorily. Although the engine would probably start quite readily with only one igniter operating, most gas turbine engines have two. However, because there are only two igniters, a means of passing the starting flame between the combustion chambers is necessary. Interconnectors, fitted between adjacent flame tubes, are used for this purpose. Immediately after light-up, the flame in the combustion chambers which have the igniters causes an increase in the pressure within those chambers. The pressure differential between a chamber which has a flame in it and those adjoining it which have no flames drives the burning gases through the interconnector pipework. When the burning gases come into contact with any unlit mixture in the adjacent combustion chamber, they ignite that mixture. This process is continued around the engine until the contents of all the chambers is burning, whereupon the pressures within them are equalized and the flow through the interconnectors ceases. A problem that occasionally happens on a gas turbine for one reason or another is that of a wet start. A wet start happens when the mixture of air and fuel in the combustion chamber fails to ignite during a start. A considerable amount of fuel will have been fed into the combustion chamber during the attempt to start. If that fuel is not removed before the next attempt to start, and if that attempt is successful, the result will be a combination of excessively high gas temperatures in the turbine region and torching, which is the name for a very long, very hot jet of flame issuing from the rear of the engine. Two methods are used for clearing the excess fuel from the engine. The combustion chambers are fitted with an automatic drain system, and an operational procedure known as a blowout cycle is used to clear any remaining traces of jet fuel from the combustion chambers, the turbine and the jet pipe. We'll now take a look at these two methods, beginning with the fuel drain system. The fuel drain system utilizes drain tubes which connect the lowest part of each chamber with the next chamber below it. Fuel remaining after a wet start will attempt to find its own level by flowing from the top of the engine to the bottom chamber. The bottom chamber contains a drain valve which is held open by a spring, allowing the fuel to leave the engine. The valve is closed by combustion chamber pressure when the engine is running. Any remaining traces of fuel within the engine must be evaporated. To this end, the engine must be motored over on a blowout cycle. During a blowout cycle, the engine is turned over by using the starter motor. It is rotated for the time normally allocated to a full start cycle, but with the high-pressure fuel cock shut and the ignition system switched off. Air from the compressor will flow through the combustion chambers, the turbine and the exhaust system, causing any remaining fuel to evaporate and be dispersed. The multiple combustion chamber system consists of a number of the individual combustion chambers, which are shown here. Each combustion chamber consists of a flame tube, which has its own air casing. The combustion chambers are disposed around the engine just to the rear of the compressor section. Most modern engines have combustion chambers which are either tubo-annular or more commonly annular in their design. However, their principle of operation is the same as that used in a basic combustion chamber. We will now look at these two types of system, beginning with the tubo-annular type. The tubo-annular combustion chamber system, shown here, is sometimes also called the cannular or can-annular system. The tubo-annular combustion chamber system differs from the multiple combustion chamber system insofar as it does not have individual air casings for each of the flame tubes. A number of flame tubes are fitted within an inner and outer air casing, which makes this system a more compact unit. This illustration is of a typical example of an annular combustion chamber system. It has a single annular flame tube, which is contained within an inner and outer casing. The annular system has several advantages over the multiple combustion chamber system and the tubo-annular system from which it was developed. They are: for the same power output, the length of the annular chamber is only 75% that of a tubo-annular system of the same diameter. This is because there is no wasted space around the combustion chambers. There are no flame propagation problems. Compared to a tubo-annular system, the air casing area is less, consequently less cooling air is required. The combustion efficiency is raised to the point where unburnt fuel is virtually eliminated, allowing the oxidization of carbon monoxide to non-toxic carbon dioxide. Because the air is spread evenly around the annulus, there is a much better pressure distribution of the gases impinging on the turbine, so it has a more even load placed upon it. Many turboshaft engines, such as those used in helicopters and as auxiliary power units, have reverse flow annular combustion chambers. In this type of engine, the final compression stage is centrifugal, so that the air delivered to the combustion chambers is being pushed out radially. This allows the combustion chamber assembly to be mounted around the turbine, with the air flowing through it in the reverse direction. This arrangement allows the engine to be much shorter, lighter and stiffer than it otherwise would be. That is the end of the lesson. Here are the main points you should take from it. The perforated flare and the swirl vanes reduce the velocity of the air entering the combustion chamber to prevent the flame being blown out. The drain tubes connect together the combustion chambers in order to provide a path for the fuel to drain from them in the event of a wet start. The primary air is mixed in a ratio of approximately 15:1 by weight with the fuel and burnt. The secondary air reacts with the primary air to form a donut or smoke ring-shaped area of flame known as a toroidal vortex. The toroidal vortex stabilizes and anchors the flame and prevents it being moved through the flame tube away from the fuel nozzle area. The tertiary air cools the gases to a maximum temperature of between 1000 and 1500 degrees Celsius, which is the maximum safe level for the turbine nozzle guide vanes. The multiple combustion chamber system consists of a number of individual combustion chambers. The tubo-annular combustion chamber system does not have individual air casings for each of the flame tubes. The annular combustion chamber system has an annular flame tube which is contained in an inner and outer air casing. The advantages of an annular system over the other systems are: for the same power output, the length of the annular chamber is only 75% that of a tubo-annular system of the same diameter. There are no flame propagation problems. Less cooling air is required. It has a higher combustion efficiency. There is a much better pressure distribution of the gases impinging on the turbine. In this lesson, we will take a closer look at the combustion process, and we will examine some of the methods used to ensure that the fuel is fully atomized or vaporized as it enters the combustion chamber. In order to obtain the maximum heat release from the burning mixture of fuel and air in the combustion chambers, the chemically correct air-fuel ratio of 15:1 by weight must be used. Whereas in the piston engine, the use of the chemically correct air-fuel ratio of 15:1 can cause detonation to occur, in the gas turbine engine it poses no such problem, because there are no large peaks of pressure to assist in its generation. The fuel and air are therefore mixed and burnt in the primary zone of the combustion chamber in the ratio of approximately 15 units of air to 1 unit of fuel by weight. The addition of secondary and tertiary air will, however, dilute the mixture to the extent that the overall ratio may vary from 45:1 to as weak as 130:1. In the introduction lesson, we stated that combustion theoretically occurs at a constant pressure. In reality, as is shown here, a small loss in pressure does occur as the gas passes through the chamber. This loss of pressure is caused by having to provide adequate turbulence and mixing. Losses vary from 3 to 8% of the pressure at the entrance to the combustion chamber. During normal engine running conditions, combustion is self-supporting. The ignition system is actually switched off as soon as the engine has attained self-sustaining speed. Self-sustaining speed is the speed at which, after start, the engine can accelerate without the assistance of the starter motor. There are, however, certain engine operating conditions which do require the ignition system to be operating continuously. For instance, when there is the risk of a flame-out, which is the extinction of the flame in the combustion chamber assembly, the ignition system is used continuously. One such occasion would be during takeoff from a heavily contaminated runway, where the ingestion of large quantities of water into the engine intakes could cause a flameout. Combustion stability means smooth burning of the mixture, coupled with the ability to remain alight over a large range of air-fuel ratios and air mass flows. This graph shows the limits of those air-fuel ratios and air mass flows within which combustion will remain stable. The graph shows that combustion stability will occur only between a narrower and narrower range of air-fuel ratios as the air mass flow through the engine increases. And beyond a certain level of air mass flow, the flame is extinguished. While the engine will run satisfactorily at any point in the stable region shown, if for any reason the engine should fail, the region in which a restart is possible is somewhat smaller. This smaller region is known as the ignition loop. A restart of the engine in the air while it is being rotated by the airflow is called a relight. Should the engine flame out at high speed, it may be necessary to slow down to reduce the mass flow of air through the engine in order to get into the ignition loop region before the engine can be successfully relit. This graph illustrates a relight envelope for an imaginary engine, showing the flight conditions under which it would be guaranteed to relight if it was fully serviceable. For a successful relight, the airflow through the engine causes it to rotate, or windmill, allowing the compressor to supply sufficient air to support combustion. All that is then required is the opening of the high-pressure fuel cock to deliver a fuel supply and operation of the ignition system to ignite the mixture. In the system shown here, ignition to relight the engine is supplied by moving the ignition switch to the flight start position. The electrical power to the relight ignition circuit functions independently from that which feeds the normal start circuit. This graph shows the combustion efficiency of a modern gas turbine engine across the range of air-fuel ratios which occur during normal operating conditions. Combustion efficiency is the efficiency with which the combustor assembly extracts the potential heat contained in the fuel. Modern gas turbine engines have a very efficient combustion cycle. At high power operating conditions, combustion efficiencies as great as 99% are achievable. And at idle, the systems will still give as much as 95%. The fuel spray nozzles have the task of atomizing or vaporizing the fuel to ensure that it is completely burnt. In order to achieve the very high levels of combustion efficiency that is required, it is essential that this task is completed fully. This is no easy undertaking considering the velocity of the airstream from the compressor and the small distance available within the chamber for combustion to occur. Early engines used a spray nozzle with a single orifice of fixed size known as a simplex nozzle. The problem with this type of nozzle is that if the orifice is large enough to produce a good spray of atomized fuel at high engine speed when a high fuel flow is required, then at lower speeds and thus lower pump output pressures, the flow through the orifice will not be fully atomized and some of the fuel will not be burned. In the worst case, the fuel may not be sufficiently atomized during engine start for light-up to occur. A number of different systems have been devised to overcome the problems associated with the simplex nozzle. We will look at 3 such systems here. Beginning with the air spray system. Shown here is a typical air spray system nozzle, which uses a high-velocity airstream from the compressor to break up the flow of fuel. The air is fed into the nozzle swirl chamber through inner swirl vanes. Here it mixes with the fuel before the mixture is sprayed out of the nozzle. The spring and distributor will prevent fuel from reaching the nozzle until there is sufficient fuel pressure for complete atomization. This system requires only a relatively low fuel pressure and can therefore operate using a gear-type engine-driven fuel pump. This type of pump is much lighter than the more sophisticated plunger-type pump which is required with other types of system. The duplex fuel spray nozzle has two concentric orifices of different sizes, a small inner primary orifice and a larger main orifice. The primary fuel line feeds the primary orifice, a relatively small hole, which is capable of providing a finely atomized spray at lower fuel pressures. With low fuel pressure, the pressurizing valve closes off the main fuel feed line. When the engine accelerates during start, fuel pressure builds until the pressurizing valve starts to open. This allows fuel to flow through the main orifice, where it will supplement the spray of fuel from the primary orifice. In this lesson, we will look at the exhaust system, through which the hot gases are ejected from the engine. The exhaust system is an often underrated part of the propulsion unit, yet its design exerts a considerable influence on the performance of the engine. The gases which discharge from the turbine must exit in the correct direction and at the optimum velocity to provide the thrust of the turbojet engine. While in the turboprop engine, where the thrust is provided by the propeller, the turbine gas temperature and back pressure at the turbine are to a large extent dictated by the design of the outlet nozzle. The three main components of the exhaust system are the exhaust cone, the jet pipe, and the propelling nozzle. The temperature of the gases entering the exhaust system can be between 550 and 850 degrees Celsius. This temperature can rise to as high as 1500 degrees Celsius if an afterburner, sometimes called a reheat system, is used. Afterburners are explained in another lesson. The fuselage of the aircraft, if it has the exhaust system running through it, as happens with most fighter jet aircraft, must be protected from these temperatures. This is done by allowing a clearance between the jet pipe and the aircraft's skin, through which air is allowed to circulate, and by insulating the jet pipe with some form of fibrous material sandwiched between thin layers of stainless steel. The velocity of the gas as it leaves the turbine can be between 750 and 1250 feet per second. This is somewhere around 0.5 Mach, or half the speed of sound. If this gas has to negotiate a long jet pipe before being ejected into the atmosphere to provide thrust, a great deal of turbulence will be caused within the pipe. This will lower the efficiency of the engine and reduce its thrust, so an effort is usually made to reduce the velocity of the gas after it leaves the turbine. This diagram shows the basic layout for the jet pipe of an aircraft without afterburners. Although the jet pipe outer casing is reducing in circumference as the gas leaves the turbine, because of the insertion of the exhaust cone, a conical-shaped device positioned close up to the turbine disc rear face, the area into which the gas is moving is in fact a divergent duct. The divergent duct reduces the velocity of the gases leaving the turbine before they pass down the length of the jet pipe, so minimizing turbulence. The exhaust cone also prevents the hot gases flowing across the rear disc face of the turbine, further reducing disturbance and preventing overheating of the disc. The rear turbine bearing is also supported inside the exhaust cone via turbine rear support struts, which are streamlined by fairings. The fairings straighten out any residual whirl which may exist in the gas stream as it exits the turbine. This residual whirl would cause additional losses through generating turbulence if it was allowed to pass into the jet pipe. The exhaust gases travel down the jet pipe and finally exit to atmosphere via the convergent propelling nozzle. In a turbojet engine, the convergent propelling nozzle increases the gas velocity to speeds of Mach 1 at virtually all thrust settings above idle. Mach 1 is the speed of sound in relation to the temperature of the gases. At this velocity, which is known as sonic speed, the nozzle is said to be choked. This means that no further increase in velocity can be obtained unless the gas temperature is increased. The static pressure of the gas reduces towards ambient as it passes through the nozzle. On some engines, particularly those flying at supersonic speeds, the hot gases exit the jet pipe through a convergent-divergent nozzle. As with the standard convergent nozzle, when the gas enters the convergent section of the convergent-divergent nozzle, its velocity increases with a corresponding fall in static pressure. The gas velocity at the narrowest point, the throat, reaches Mach 1. As the gas flows into the divergent section, it expands as its pressure progressively falls towards atmospheric. This accelerates the gas beyond Mach 1 towards the open exit. The reaction to this increase in velocity is a pressure force acting on the inside wall of the nozzle. A component of this force, which acts parallel to the longitudinal axis of the nozzle, produces a further increase in thrust. Bypass engines have two gas streams to pass to atmosphere. This makes the exhaust system of this type of engine a slightly more complex affair when compared to the essentially simple systems we've examined so far. The low-ratio bypass engine exhaust, shown here, combines the bypass air and the hot core gases in a mixer unit. The mixer unit ensures thorough mixing of the two gas streams before they are ejected into the atmosphere. This picture shows the two methods which are used to exhaust the cold bypass air and the hot exhaust gases in the high-ratio bypass engine. The top illustration shows a method whereby the hot and cold nozzles are coaxial and the two streams mix externally. Greater efficiency can, however, be obtained by fitting an integrated exhaust nozzle, which is depicted in the lower illustration. Within this type of unit, the two gas flows are partially mixed together before their ejection into the atmosphere. This diagram shows relative sound levels from various sources, some of the highest among them being pure turbojet aircraft engines. Although an aircraft's overall noise signature is a combination of sounds which stem from many sources, the principal agent is the engine. Airport regulations and aircraft noise certifications governing the maximum noise level which aircraft are allowed to produce have forced rigorous research into ways of reducing that noise. In fact, many of the older, noisier pure turbojet engine aircraft are banned from civil airports in many countries. The most significant sources of noise from the engine are the compressor, the fan in high-ratio bypass engines, the turbine, and the exhaust. Although the noises which emanate from these various sources all obey slightly different laws and mechanisms of generation, their levels all increase with greater relative airflow velocity. The relative speed difference between the exhaust jet and the atmosphere into which it is thrusting causes a shearing action. The shearing action, in turn, creates a violent and extremely turbulent mixing pattern. Here, where the turbulent zone is narrow, is where high-frequency noise is being generated in the mixing pattern. And here, where the turbulent zone has widened, low-frequency noise is generated. The noise of the exhaust of a pure turbojet is of such a high level that the noise of the compressor and the turbine is insignificant, except at very low thrust conditions. To be allowed to continue flying, the operators of older pure turbojet aircraft have had to find some system of reducing their noise output. Aircraft can still be seen with devices known as hush kits fitted to engines. One such piece of equipment is the corrugated internal mixer. This device mixes the exhaust gas with external air in the extended exhaust pipe. The corrugated internal mixer is very efficient at reducing exhaust noise, but unfortunately it also induces performance penalties which limit its popularity with aircraft operators. The level of noise from the exhaust is more affected by a reduction in its velocity than the noise levels of either the compressor or the turbine are. It is logical, therefore, to expect that a reduction in exhaust jet velocity will have a stronger influence in reducing noise levels than an equivalent reduction in either compressor or turbine speeds. The exhaust noise of a bypass engine drops because of the much lower velocity of the bypass air, but because its power output is much greater, the turbines and the low-pressure compressor of a large bypass engine generate a higher noise output. In the case of a high-ratio bypass engine, say an engine with a 5:1 bypass ratio, the noise from the jet exhaust is reduced to such a degree that the noise from the low-pressure compressor and fan and the turbine are now predominant. Great efforts have been made in these types of engine to reduce the noise coming from the fan and the turbine. The use of the type of noise-absorbing material, which is shown here in the engine intake and the bypass duct, is extremely efficient in reducing noise in those regions. Further down the engine, in the hotter zones, slightly different materials are used to great advantage in the same quest for noise reduction. The disadvantage of the use of these materials is that they add a small percentage in weight and that their skin friction is slightly higher than the material that would otherwise be used. Together, these factors cause a slight increase in engine fuel consumption. The area around operating gas turbine engines is inherently dangerous to personnel and equipment. This diagram indicates the primary danger zones around the intake and exhaust of an engine similar to the type fitted on the Cessna Citation. The more powerful the engine, the further these zones will extend from the engine. Notice that the gas velocity exiting the engine is extremely high, as is its temperature, although the levels of both drop quite dramatically with increasing distance from the exhaust nozzle. Foreign object ingestion is an ever-present danger to gas turbine engines. This graphic illustrates an event which happened at Los Angeles in 2009. It shows a baggage container which was sucked into the intake of an engine of a taxiing Boeing 747. The area behind an operating gas turbine engine is just as dangerous as the intake area. This graphic illustrates an experiment carried out in which a car was driven behind a Boeing 747 when the engines were producing takeoff power. Pilots should be extremely careful with the amount of power they use when taxiing around often very crowded ground maneuvering areas. That is the end of the lesson. Here is a summary of the main points. The three main components of the exhaust system are the exhaust cone, the jet pipe and the propelling nozzle. The temperature of the gases entering the exhaust system can be between 550 and 850 degrees Celsius. The velocity of the gas as it leaves the turbine can be between 750 and 1250 feet per second. This is somewhere around 0.5 Mach, or half the speed of sound. A divergent duct reduces the velocity of the gas as it enters the turbine. The exhaust cone prevents the hot gases flowing across the rear turbine disc face, reducing disturbance and preventing overheating of the disc. The convergent propelling nozzle increases the gas velocity to speeds of Mach 1 in a turbojet engine at virtually all throttle openings above idle. At this velocity, sonic speed, the nozzle is said to be choked. The low-ratio bypass engine exhaust combines the bypass air and the hot exhaust gases in a mixer unit. In a high-ratio bypass engine exhaust system, the hot and cold nozzles may be coaxial, with the two streams mixing externally. Greater efficiency can, however, be obtained by fitting an integrated exhaust nozzle. Pure turbojet engines may have hush kits fitted to their exhaust system to reduce their noise. These kits improve the mixing of the exhaust gas and atmospheric air. The exhaust noise of a bypass engine drops because of the much lower velocity of the bypass air. The use of noise-absorbing material in the engine intake and the bypass duct is extremely efficient in reducing noise in those regions. In this lesson, we will be looking at gas turbine engine reverse thrust systems. Modern aircraft braking systems, which incorporate sophisticated anti-skid units, are extremely efficient. However, poor runway conditions can reduce the capability of even the most refined braking system. A reverse thrust system, where the power of the engine is used to oppose the motion of the aircraft, can reduce the stopping distance, and in circumstances where stopping distance is not a problem, it can help to reduce wear and heating in the brake system. The usual method of operating the reverse thrust system is to select it immediately the weight of the aircraft is firmly on the main wheels. As can be seen from the diagram, the use of reverse thrust in this way can reduce the landing distance dramatically. There are three basic types of thrust reversal systems presently in use. They are the clamshell door system, the bucket or external door system, and the cold stream reverser or blocker door system. All these types of thrust reversal system are typically operated by hydraulic or pneumatic actuators or motors. All three systems reverse the direction of some or all of the gas flow, thereby reversing the thrust. We will now take a closer look at each type of system, beginning with the one using clamshell doors. The name clamshell has been applied to this system of reverse thrust because of the shape of the reverser doors, which resembles that of a clamshell. In the clamshell door system, the reverser doors are usually pneumatically operated. They use high-pressure compressor air as the power source. Pneumatic rams move the reverser doors from their stowed, forward thrust position to their deployed, reverse thrust position. In their stowed position, the clamshell doors cover guide vanes known as cascade vanes, which are revealed when the doors move to the deployed state. While they are deployed, the clamshell doors shut off the normal exhaust gas exit, forcing the gas to escape through the cascade vanes in a forward direction, so that the forward motion of the aircraft is opposed by the reverse thrust thus generated. The cascade vanes are aiming the exhaust mainly in a forward direction, but they are angled so that the exhaust has an outboard angular component as well. This outboard angular component minimizes the chances of debris and hot gases being re-ingested into the engine intake during the use of reverse thrust. The external door or bucket reverse thrust system is normally hydraulically operated. The rear portion of the engine exhaust pipe is shaped like two halves of a bottomless bucket, which are hinged to enable them to swing rearwards when selected, to deflect the exhaust gas forward. The cold stream reverser or blocker door system is only used on high bypass ratio fan jet engines. The essential difference between the blocker system and both the clamshell door and bucket reversing systems is that, while the latter reverse the direction of the hot exhaust gases, the blocker system blocks and diverts the cold bypass air stream only. This system is usually powered by engine bleed air through air-driven motors. The output of the air motor drives flexible shafts which operate the blocker doors. When the blocker doors are closed, they block off the rearward movement of the bypass air and expose cascade vanes which direct the air in a forward direction. Operation of the reverse thrust system is initiated by the movement of reverse thrust levers in the cockpit. Each engine with a reverse thrust capability has a reverse thrust lever, which is normally mounted on the forward part of the engine thrust lever or throttle. With the lever fully forward or down, the reverse thrust system will be in the stowed or forward thrust position. The first upward or rearward movement of the lever will move the reverse thrust system to the deployed or reverse thrust position. This is often known as the reverse idle position. By moving the lever rearwards or upwards from this position, the reverse thrust can be increased as required, up to the limit specified in the Aircraft Operations Manual. To cancel reverse thrust, the lever is moved fully forward or down. This will cause the system to move back to its stowed or forward thrust position. In order that the pilot may have information regarding the position of the reverser doors, some form of warning is fitted. The warning can be amber lights positioned within full view of the crew, or captions which appear on the pilot's electronic screens. The warnings will be shown whenever the reverser doors are unlocked and are between their stowed, forward thrust, and their deployed, reverse thrust, positions. Other indications regarding the reverse thrust system may be provided. There may, for instance, be a green light to indicate when the system is fully deployed. Safeguards have to be built into the reverse thrust system, which will protect the aircraft in case of a malfunction or incorrect handling. There are 5 safeguards usually built into the system. They are: reverse thrust cannot be selected on an engine until the throttle lever of that engine is at idle. Reverse thrust cannot normally be activated on an aircraft until that aircraft is on the ground. This is usually achieved through the landing gear air-ground logic interlock system. Some Boeing aircraft allow reverse thrust to be selected when the radio altimeter indicates less than 10 feet above ground level. With reverse thrust selected, engine power cannot be increased above idle power until the reversed thrust doors are in the deployed or reverse thrust position. If, while forward thrust is selected, the reverser doors inadvertently move to the deployed position, the throttle will automatically close to idle. If, while reverse thrust is selected, the reverser doors inadvertently move to the stowed or forward thrust position, the reverse thrust lever will automatically go to the deployed or reverse idle position. While there is normally no restriction on the upper speed at which reverse thrust can be selected, there may be a minimum speed below which operation of the reverse thrust system is prohibited, except in an emergency. Earlier, it was described how the reverse thrust was angled forwards and outwards. This was to minimize the chances of debris and hot gases being re-ingested into the engine. There is, nevertheless, a danger that, despite the angle of the cascade vanes, if the aircraft is only moving forward slowly or is stationary, the exhaust gas stream and any associated debris may be sucked into the compressor, with potentially catastrophic consequences for the engine. To prevent the likelihood of this happening, the standard operating procedure on some aircraft is to reduce the position of the reverse thrust lever to the reverse idle position at, typically, 60 to 80 knots. Subsequently, at a speed where it is considered there is no further benefit to be gained from maintaining that idle reverse position, i.e., when it is judged that there is no further requirement for a sudden selection of full reverse power, usually at about 50 knots, the reverse thrust lever is returned to the stowed position. When the reverse thrust system is in use, engine indications must be closely monitored, in particular the exhaust gas temperature. It should be borne in mind that re-ingestion of the exhaust gas will cause the EGT to increase, perhaps exacerbating a situation where high ambient temperatures are already causing EGT to be close to its limit. Care must be exercised when increasing reverse RPM that the engines respond symmetrically, as yaw can be induced if they are not. This could be particularly embarrassing when applying full reverse thrust when landing on a slippery runway. There may also be a performance limitation imposed if one engine thrust reverse system is inoperative, as the total reverse capability will be reduced, and on an aircraft with two wing pod mounted engines, having one engine thrust reverse system inoperative may mean that the remaining serviceable reverser cannot be operated either, because of the asymmetric effect it would impart upon selection. That is the end of the lesson. Here is a summary of the main points. A reverse thrust system can reduce the aircraft's stopping distance, and where stopping distance is not a problem, it can help to reduce wear and heating in the brake system. In the clamshell door system, the reverser doors are usually pneumatically operated by high-pressure compressor air. The external door or bucket reverse thrust system is normally hydraulically operated. The cold stream reverser or blocker system is only used on high bypass ratio fan jet engines. It blocks and diverts the cold bypass airstream only. This system is usually powered by engine bleed air through air-driven motors. Cascade vanes aim the exhaust mainly forward, but they are angled so that the exhaust also has an outboard angular component which reduces the chances of debris and hot gases entering the engine intake. Each engine with a reverse thrust capability has a reverse thrust lever which is normally mounted on the forward part of the engine thrust lever or throttle. So that the pilot has information about the position of the reverser doors, a warning and indicating system is fitted. 5 safeguards protect the aircraft in case of a malfunction or incorrect handling. There may be a minimum speed below which operation of the reverse thrust system is prohibited, except in an emergency. Care must be exercised when increasing reverse thrust so that the engines respond symmetrically, as yaw can be induced if they do not. A performance limitation may be imposed if one engine thrust reverse system is inoperative.
In order that we can calculate the performance level of any gas turbine engine, specific symbols are used to denote the pressures and temperatures at various locations throughout the engine. Some of these symbols are shown in this diagram. These symbols vary slightly for different types of engine. We've learnt that thrust is obtained from the reaction derived by accelerating a mass of air backwards, thereby achieving forward thrust. In accordance with Newton's third law, for every action there is an equal and opposite reaction. If we examine the formula, in our case the force we require is thrust, so we can restate the equation in this manner. When W equals the mass of air in pounds, V1 is the inlet velocity in feet per second, and VO is the exit velocity in feet per second. In the case of a turbojet running in a choke condition, there will be the addition of pressure thrust, which will give us this. The power of a turbojet can be measured as thrust. Thrust is displayed on either a P7 or an engine pressure ratio gauge, both of which are thrust gauges. The engine pressure ratio, or EASA, is the ratio of the pressure in the jet pipe of the engine, which we call P7, to that at the intake of the engine, which we call P1. The power output of a fan engine can be shown on a gauge which measures the ratio of the integrated values of the turbine discharge pressure and the fan outlet pressure to the compressor inlet pressure. The output of a turboprop is measured in shaft horsepower, or SHP, produced at the propeller shaft. The engine's torque, or turning moment, is proportional to its shaft horsepower. Torque is displayed on a torque meter. P7, EASA, and torque meters are all covered in engine instrumentation. Thrust equivalent horsepower, or TEHP, is the unit of power used to describe the power output of turboprop engines, and also some turboshaft engines. In practice, there is always a certain amount of jet thrust in the output of a turboprop engine. The equivalent shaft horsepower of a turboprop engine is derived by adding its shaft horsepower output to any horsepower obtained from its jet thrust. Under static conditions, 1 shaft horsepower equals approximately 2.6 pounds of thrust. We saw from the earlier equation that thrust was proportional to the mass flow rate of air through the engine, and the acceleration we could impart on that air mass flow. Both the mass flow and the acceleration will be affected by changes in altitude, temperature, and airspeed, which all have a bearing on the efficiency of the engine, and therefore the gas energy available for conversion into either thrust horsepower or shaft horsepower. To be economical, an engine must maintain the ratio of its fuel consumption to either its thrust or its shaft horsepower at as low a level as possible. This ratio is termed the specific fuel consumption, or SFC, of the engine. Specific fuel consumption is measured in pounds of fuel used per hour per pound of thrust or shaft horsepower. The specific fuel consumption is determined by both the engine's thermal and its propulsive efficiency. The amount of thrust produced by a turbojet is proportional to its RPM. Engines which have either a single spool axial flow compressor or a centrifugal flow compressor, and some engines with a combination of centrifugal and axial flow compressors, have a linear relationship between their RPM and the thrust they develop. This linear relationship is shown in this diagram. Engines which have twin spool compressors have a slightly different relationship between RPM and thrust developed. This happens because optimum compressor blade efficiency and compressor ratio are designed to occur at higher RPMs that are normally utilized during the cruise, where the engine spends most of its working life. The relationship between RPM and thrust becomes non-linear, as shown in this diagram. This diagram illustrates that the highest 30% of the thrust is obtained with the RPM above 90% RPM. The ground idle HP RPM of a twin-spool engine is in the order of 58 to 62%, and the LP RPM idles on the ground at about 25%. In flight, these idle values will be higher because of the windmilling effect caused by the forward airspeed. In a high bypass ratio turbofan engine which is running at an idle power setting, the fan speed, or N1, is 25% of its maximum value. The engine will generate approximately 5% of takeoff thrust at this power setting. The different levels of engine power are nominated by the following terms. Takeoff thrust. Maximum thrust available from the engine. This power setting is normally time limited. Go around thrust. This power setting can be the same as that for takeoff thrust, but it's normally a slightly lower value. Maximum continuous thrust. This power setting is the maximum level that can be used continuously. Maximum climb thrust. This power setting is equivalent to max continuous thrust, and is selected to give the best angle of climb speeds. Maximum cruise thrust. This is a power setting below the value of maximum continuous thrust. Maximum cruise thrust can be used, for instance, if the aircraft has to climb more quickly than normal because of a terrain clearance requirement, or in order to respond to a request from ATC for a higher rate of climb. As aircraft altitude increases, temperature, pressure, and density all decrease. The thrust of a gas turbine engine depends upon accelerating a mass of air rearwards. If the density of that air, and thus its mass, is decreasing with increasing altitude, then the thrust generated by that engine must also decrease as the aircraft climbs. Most sophisticated gas turbine engines, which are fitted in aircraft, incorporate an element in the fuel control unit to reduce the fuel flow to match the reduced air mass flow in the climb. This assists in maintaining a constant engine speed for a fixed throttle position. The fall of temperature with altitude increase has a second effect on engine thrust. Because of this reduction of temperature, the air density does not reduce as much as it otherwise would, under the influence of the pressure drop alone. This, to some extent, compensates for the loss of thrust caused by the reduction in pressure. This compensation continues to have effect until the tropopause, which is at 36,089 feet. At altitudes between the tropopause and 65,617 feet, the temperature remains constant at minus 56 degrees Celsius. Thus, at these altitudes, the thrust is affected by pressure alone. This graph demonstrates that the specific fuel consumption remains almost constant with altitude increase. This is because the fuel flow reduces at about the same rate as the thrust reduces as the aircraft climbs. As aircraft altitude increases and the density of the atmosphere reduces, a turboprop engine suffers a similar loss of power to that of a turbojet engine. We showed earlier that the output of a turboprop engine is a combination of its shaft horsepower and any jet thrust that the engine can produce. These graphs show that at a constant airspeed, both the shaft horsepower and the jet thrust of a turboprop engine reduce with increasing altitude. The result of this is that the thrust equivalent horsepower, which is the combination of shaft horsepower and jet thrust, will also reduce with increasing altitude. This graph shows that the specific fuel consumption of a turboprop engine improves as the aircraft climbs to approximately 20,000 feet, but then it increases again as the aircraft climbs towards 35,000 feet. We've already noted that on a hot day the air density will be lower than the international standard, and thus, as we saw from the simple form of the thrust equation, the thrust developed by an engine running at a given RPM will decrease below the level it would attain on an EASA day. However, because it's hot, the air is less dense, and this means that the load on the turbine, as it attempts to drive the compressor at that given RPM, is less. The engine will thus require less fuel to maintain that RPM. Or, alternatively, the engine will run more quickly if the fuel flow is maintained at the same level. On the other hand, on a day when the ambient temperature is below EASA, the density of the air will increase, and the thrust developed for a given engine RPM will also increase. The load on the turbine will have increased because of the increased density of the air passing through the compressor. So, to maintain the given RPM, the fuel flow required will have to be increased. Or, alternatively, if the level of the fuel flow is maintained, the engine will run more slowly. In cold ambient conditions, when the air is denser than EASA, the engine will develop its required takeoff thrust before the limiting compressor RPM and turbine gas temperature are reached. However, opening the throttle any further to take advantage of any extra thrust which may be available will have no effect because of an element of the fuel control unit called the power limiter. The power limiter prevents the compressor output exceeding a set maximum pressure, thus safeguarding the integrity of the compressor casing. Engines which have the ability to achieve takeoff rated thrust at less than full throttle when ambient temperatures are below EASA are called part throttle or flat-rated engines. From examination of the simple thrust equation, it would appear that, as the aircraft flies faster, if the exit velocity remains the same with an increasing inlet velocity, the thrust will decrease. However, we know from the air intake lesson that the engine air intake is designed so that as the aircraft forward speed increases, the ratio between the total air pressure at the air's entry to the compressor and that of static air pressure at the air intake entry increases. This increases the mass flow through the engine and the exit velocity of that air from the engine. This effect starts to make its presence felt as the aircraft speed reaches between 0.1 and 0.2 Mach. These graphs illustrate that as airspeed increases, the ram effect into the intake of a turboprop engine causes its shaft horsepower to increase, while its net jet thrust decreases. The overall effect on the thrust equivalent horsepower of these two changes is shown in this graph. This concludes the lesson on engine performance.
The engine accessory gearbox provides the power to drive hydraulic pumps, electrical generators and possibly pneumatic pumps, all of which are used to supply services both on the engine and in the aircraft. It also drives fuel pumps, oil pumps, speed sensing devices and other components necessary for efficient engine operation, as well as providing a mounting for the engine starter motor. In this lesson, we will look at where the accessory gearbox is located and how it is driven. The drive for the accessory gearbox is usually taken from the high-pressure compressor shaft, through a radial shaft, which is connected via an internal right-angle drive gearbox. The radial shaft connects to the external gearbox, which provides mountings and drives for the accessories. The internal gearbox which takes the drive from the compressor shaft uses bevel gears in order to change the direction of the drive. The compressor shaft expands and contracts axially during its working cycle, and unless action is taken to prevent it, this axial movement will pull the bevel gears apart, causing drive to the accessories to be lost and also causing damage to the teeth of the bevel gears. This diagram shows one of the methods currently in use to maintain the teeth of the bevel gears in close contact with each other. In this method, the compressor shaft is splined, that is to say, it has grooves cut into it, which run parallel to the shaft's axis. And a short shaft, known as a stub shaft, which has teeth cut internally that conform to the pattern of the grooves in the compressor shaft, is fitted around it. The accessory gearbox drive bevel gear is fitted on the stub shaft. The stub shaft is held firmly in the correct axial position by its location bearing. The stub shaft will rotate with the compressor shaft, and the splined compressor shaft can move axially inside the fixed stub shaft. This means that the gear teeth will not lose contact with each other as the compressor shaft moves. An alternative system to the stub shaft drive uses an idler gear shaft, which is held firmly in position by location bearings. One end of the idler gear shaft is connected to a wide-toothed spur gear fitted to the compressor shaft, and the other end is fitted with a bevel gear which meshes with the radial drive shaft to the accessory gearbox. Because of its width, the spur gear can accommodate the axial movement of the compressor shaft without losing contact with the idler gear drive. In an effort to spread the load of driving accessories, some engines divide the accessory gearbox into two smaller separate gearboxes. As well as the drive from the high-pressure compressor shaft, a second radial shaft may be taken from the low-pressure compressor shaft, which is rotating at a slower speed and used to drive a second external gearbox. This two-gearbox system has a second advantage of allowing the accessories to be divided into two smaller groups, thus overcoming the difficulties of limited space around the engine. During engine start, the starter motor, which is mounted on the accessory gearbox normally driven by the high-pressure compressor shaft, reverses the normal drive situation. Instead of the gearbox being driven by the engine, the gearbox is now the driving force on the engine. The starter motor thus causes the high-pressure compressor shaft to rotate, and the low-pressure compressor shaft is rotated subsequently by air being drawn through the engine. Accessories which are specific to the engine's operational needs, such as the oil pumps and the fuel pumps, need to be driven from the same gearbox as that to which the starter motor is connected. The gearbox connected to the high-pressure spool is known as the high-speed external gearbox because it is being driven by the shaft which is rotating at the highest speed of all. Logically, the other accessory gearbox is called the low-speed external gearbox. Having to fit the gearbox around the engine means that the accessory gearbox usually has a curved banana-like shape. For ease of access during servicing, when only one accessory gearbox is fitted, it is usually located on the underside of the engine. This picture shows an accessory gearbox and some of the associated accessories. Worthy of interest are the oil pumps, which are contained in an oil pump pack, a unit which contains one pressure pump and a number of scavenge pumps. In some engines, as many as 6 scavenge pumps may be contained in an oil pump pack. The width of the gear teeth in this gearbox indicates that the greatest load from driving the accessories is taken on the right side of the gearbox, while the thinner teeth on the left side gear wheels show that their loads are much smaller. This grouping of small and large loads enables an efficient distribution of the drives for the minimum weight. Mechanical failure of an accessory could possibly cause the failure of the whole gearbox, and because the engine fuel and oil pumps are driven by that gearbox, this will cause the associated engine to fail. To prevent this problem, the mechanical equivalent of an electrical fuse is fitted to some of the accessory gearbox output drives. A weak section is machined into the drive shaft. This weak section is known as a shear neck. The shear neck is designed to fail if it incurs a load which is approximately 25% in excess of the normal maximum load for the particular component being driven by that shaft. In circumstances of excessive overload, the shear neck will break, allowing the individual component to stop rotating while the rest of the gearbox and accessories continue as normal. This feature is not utilized in the drives of primary engine accessory units, such as the oil pump pack or the engine high-pressure fuel pumps, because any failure of these components would necessitate the immediate shutdown of the engine. That is the end of the lesson. Here is a summary of the main points. The engine accessory gearbox provides the power to drive hydraulic pumps, electrical generators, and possibly pneumatic pumps, all of which are used to supply services both on the engine and in the aircraft. It also drives fuel pumps, oil pumps, speed sensing devices, and other components necessary for efficient engine operation. It provides a mounting for the engine starter motor. A weak section, known as a shear neck, is machined into the drive shaft to some of the gearbox output drives. The drives to the oil and fuel pumps don't have shear necks because any failure of these would require the immediate shutdown of the engine. The air-fuel mixture in the combustion chamber is ignited on engine start by an electrically powered igniter plug. The power supply for the plug is produced by a high-energy ignition unit, or HEIU. In this lesson, we will look at how the ignition system is used, and we will examine the construction and operation of the HEIU and igniter plug. All gas turbine engines have a dual ignition system fitted, which means that they have two high-energy ignition units. The high-energy ignition units each feed separate igniter plugs. This provides redundancy in the event of a failure in either system. Each high-energy ignition system has an output of approximately 12 joules. The joule is the standard international unit of energy. In electrical terms, 1 joule is equal to 1 watt per second. It may sometimes be necessary to help prevent engine flame-out to have the ignition system selected in circumstances other than engine starting. For instance, during takeoff from contaminated runways or flight through heavy precipitation, the ignition may be used continuously. The continuous use of the high-energy ignition system will cause the igniter plug to erode quickly, and this will shorten its working life. To minimize erosion of the igniter plugs, some aircraft engines are fitted with a combination ignition system, which includes a low-energy, 3 to 6 joules, continuous selection, as well as the high-energy, 6 to 12 joules, starting selection. The starting ignition system is activated when the engine start sequence is initiated, either automatically or by the operation by the pilot of the high-pressure fuel cock, start lever, or fuel and ignition switch. The igniters are either manually or automatically deactivated at some point after the engine reaches self-sustaining speed, possibly by the operation of a speed switch incorporated in the high-pressure compressor RPM indicator system. Some aircraft have an ignition system which can be operated automatically. With the ignition switch in the automatic position, if an aircraft stall is detected, the aircraft stall warning system will automatically select the continuous ignition system on. The circuit shown here illustrates all of the components within a high-energy ignition unit, which is supplied by 28 volts direct current. The main components are the transformer, which has primary and secondary windings, the trembler mechanism, the rectifiers, the reservoir capacitor, the discharge gap, the choke, the discharge resistors, and the safety resistors. We will now look at how the components work together to produce a high-energy spark at the igniter plug. With the supply connected, the primary coil and the trembler mechanism are fed with 28 volts direct current. The purpose of the trembler mechanism is to change the direct current input into alternating current. The primary coil acts as the coil of an electric relay, with the trembler switch contacts fixed to the armature. When power is applied, current flows through the coil and the switch contacts, which are spring-loaded to the closed position. A magnetic field is induced in the coil, pulling down the armature. This opens the contacts and stops the current flow, collapsing the magnetic field. The armature now moves back up and the contacts close, starting the process again. This causes the primary coil current to be constantly rising and falling in what is known as a sawtooth waveform. This sawtooth waveform is a very crude form of alternating current. The purpose of the primary capacitor is to reduce electrical arcing across the contacts of the trembler switch. The secondary coil is placed in close proximity to the primary. It has a much greater number of turns of wire than the primary coil, and together the two coils form a step-up transformer, boosting the alternating current voltage in the primary coil to 25,000 volts in its secondary coil. A transformer is an electrical device which changes alternating current of one voltage to another voltage. Transformers are fully explained in the electrical system lessons. The 25,000 volts alternating current is changed back to direct current by the diode rectifiers. Diode rectifiers are solid-state semiconductor devices which allow current to flow in one direction only. The direct current charges the reservoir capacitor. A capacitor is a device that stores electrical charge. Again, capacitors are fully described in the electrical system lessons. As the value of the charge in the reservoir capacitor builds up, it eventually reaches a level that causes a spark to jump the discharge gap. The discharge gap is inside an evacuated tube. The fact that the tube is evacuated means that changing conditions of humidity and altitude will have no effect on the voltage required to jump the gap within the tube. Consequently, the power of the spark at the igniter plug will be constant regardless of ambient conditions. The electrical energy which has crossed the discharge gap has then to flow through the choke. The choke is a coil which acts as an inductance. One of the properties of an inductance is that it opposes changes in current flow through it. This has the effect of slowing down the flow of current through it. Slowing the rate of current flow makes the duration of the spark longer. The current then passes to the igniter in the combustion chamber, where it is used to produce the spark which ignites the mixture. If the HEIU has to be removed from the engine for servicing, any charge which may remain in the reservoir capacitor, even after the electrical power to the unit has been disconnected, could be lethal. The discharge resistors act as a safety device by allowing energy trapped in the reservoir capacitor to leak away to earth in about 1 minute once the supply has been removed. The safety resistors act as a kind of safety valve if the igniter plug becomes disconnected. If the igniter plug did become disconnected, energy would continue to build up in the reservoir capacitor. The buildup of energy in the capacitor could eventually cause it to explode. To safeguard against a potentially engine-disabling explosion, the safety resistors allow energy in excess of the normal level to flow through them, thus limiting the charge stored in the reservoir capacitor. The normal spark output rate of the high-energy ignition unit is between 60 and 100 sparks per minute. However, the production of sparks from each HEIU is independent of the other, and if relight is selected with the aircraft on the ground, anyone listening at the jet pipe before engine start should hear an unsynchronized beat if both ignition systems on the engine are working correctly. As well as the direct current high-energy ignition unit that we have seen, there are transistorized high-energy ignition devices where the trembler mechanism is replaced by an electronic circuit which converts the direct current supply to alternating current. The advantage of this type of unit is that there are no moving parts. For aircraft which have an alternating current electrical system, there are units which will work on that supply. Because the input supply is alternating current, it can be fed directly to the primary coil without the need for a trembler mechanism. There are two types of igniter plug. The older of these two types works in a similar manner to that of the piston engine spark plug, but it has a much bigger spark gap. The voltage required to jump this gap is approximately 25,000 volts. This extremely high voltage requires very good insulation standards both within the unit and in the cabling to the igniter. A more modern version of the igniter plug is the surface discharge igniter plug, shown here. The end of the insulator of the surface discharge igniter plug is formed from a semiconductor material. Semiconductors are once again fully explained in the electrical system lessons. The semiconductor material allows an electrical leakage to occur between the electrode and the body of the igniter. The electrical leakage ionizes the surface of the semiconductor material, which provides a relatively low resistance path for the energy stored in the reservoir capacitor. The discharge takes the form of a high-intensity flashover from the electrode to the body of the igniter, which only requires approximately 2000 volts. That is the end of the lesson. Here is a summary of the main points. In order to provide redundancy, each engine has two separate ignition systems. To minimize erosion of the igniter plugs, some engines have a low-energy continuous ignition selection. On start, the ignition system is activated automatically, or by pilot operation of the HP fuel cock, start lever, or fuel and ignition switch. The igniters are deactivated after the engine reaches self-sustaining speed. On some aircraft, if a stall is detected, continuous ignition is automatically selected. The purpose of a direct current HEIU trembler mechanism is to change the direct current input into alternating current. A transformer boosts the voltage in the HEIU primary coil to 25,000 volts in its secondary coil. The 25,000 volts alternate current is changed back to direct current by the rectifiers. The direct current charges the reservoir capacitor. The charge in the reservoir capacitor reaches a level that causes a spark to jump the discharge gap. The HEIU discharge resistors allow energy trapped in the reservoir capacitor to leak away to earth once the supply has been removed. The HEIU safety resistors allow energy in excess of the normal level to flow through them, thus limiting the charge stored in the reservoir capacitor. The spark-type igniter plug is similar to a piston engine spark plug, but it has a much bigger spark gap. In the surface discharge igniter plug, the discharge takes the form of a high-intensity flashover from the electrode to the body of the igniter, which only requires approximately 2000 volts.
The first recorded use of an auxiliary power unit was on a four-winged interceptor aircraft in the Great War in 1916. The aircraft, called the Nighthawk, was designed and built by the owner of the firm that would eventually become Supermarine, the builders of the Spitfire. A gasoline-fueled piston engine was used in this particular instance. However, because aircraft in general, and commercial aircraft in particular, began to need more powerful electrical and hydraulic supplies and air conditioning facilities to service them while they were on the ground with their engines shut down, the auxiliary power unit, which was to satisfy these requirements, became more sophisticated. Aircraft manufacturers and operators also recognized the fact that because it had an auxiliary power unit, it also meant that the aircraft was no longer dependent on expensive ground support equipment. The auxiliary power unit can provide the necessary power for operation of an aircraft's electrical, hydraulic, and pneumatic systems. While earlier aircraft used the piston engine to drive their auxiliary power units, it soon became obvious that the gas turbine engine was safer, lighter, quieter, and more reliable. The gas turbine engine auxiliary power unit uses AVTUR, which is the same fuel as the main engines use, so the problem of fuel storage and fuel management systems is minimized. The type of gas turbine engine normally used to drive auxiliary power units is a turboshaft engine with a free turbine. The free turbine, which is designed to run at a constant speed, drives the accessories via a gearbox. The fact that the free turbine runs at a constant speed ensures that the auxiliary power unit's generator maintains a constant frequency without the need for an additional constant speed drive unit. Some aircraft use air bled from the auxiliary power unit's compressor to power the aircraft's pneumatic system, but it's also common for the free turbine to drive a separate load compressor to supply bleed air. The auxiliary power unit is normally positioned in the tail of the aircraft, where its operation will not harm personnel working in proximity to the aircraft. The auxiliary power unit of modern aircraft can be operated in the air, thus providing a backup source of power to the aircraft systems in the event of an engine failure. This ability to operate while airborne has become more important with the introduction of twin-engine aircraft, which are now flying long-haul routes under extended twin operations (ETOPS) regulations. Auxiliary power units fitted to ETOPS aircraft must be extremely reliable, as they are used in place of the failed engine to supply backup electrical and pneumatic power during single-engine operations. While other auxiliary power units may or may not have the ability to be started while the aircraft is in flight, ETOPS-compliant auxiliary power units must be capable of being started at all altitudes. If such auxiliary power units malfunction, the aircraft cannot be released for ETOPS flight and must fly a longer route. While, for example, the L-1011 TriStar can start its auxiliary power unit up to 25,000 feet and has the capability of delivering power up to 31,000 feet, the Allied Signal auxiliary power unit, which is fitted in some Boeing 737 aircraft, has a 41,000-foot start capability and can deliver 66 kVA at this altitude. If the aircraft descends to 31,000 feet, that same auxiliary power unit can deliver 90 kVA. Other 737 aircraft may have Garrett or Sunstrand auxiliary power units fitted. These units have a maximum recommended start altitude of 25,000 feet and are only rated at 55 kVA. These two auxiliary power unit control panels from the Boeing 767 and the Airbus A320 aircraft illustrate that the pilot has very little control or indication of what's happening on the auxiliary power units fitted to modern aircraft. On older aircraft, such as the earlier Boeing 737 series, the auxiliary power unit panels incorporate load meters and EGT gauges, as well as indicator lights which warn of low oil quantity, low oil pressure, high oil temperature, and overspeed. The auxiliary power unit's turboshaft engine is started by an electric starter motor powered from the aircraft battery, although some later model aircraft have a dedicated auxiliary power unit battery to preserve the aircraft batteries. When the auxiliary power unit is started, the RPM and EGT must be allowed to stabilize before it's used to power the aircraft systems. It is possible on older aircraft to see the RPM and EGT gauges. On more modern aircraft where gauges are not available, it may be possible to hear the APU RPM stabilize. The stabilization of the EGT should follow that very closely. The auxiliary power unit may not be able to completely power all of the aircraft systems. For instance, on some aircraft, the galley power will be load-shed automatically if the auxiliary power unit load reaches a maximum value. Additionally, if the auxiliary power unit EGT reaches a predetermined figure, then the bleed air valve will begin to close, reducing the ability of the auxiliary power unit to supply the pneumatic system. It's usual for the auxiliary power unit to be operated for a cooling period of at least 1 minute with no pneumatic load prior to shutdown. The auxiliary power unit will automatically shut down for the following reasons: fire, low oil pressure, high oil temperature, overspeed. The auxiliary power unit has only one fire bottle, which uses Freon, stored at a pressure of approximately 800 psi as the extinguishant. operation of the auxiliary power unit fire handle passes an electrical supply through a cartridge, which ruptures a diaphragm in the outlet of the bottle. When the diaphragm breaks, the internal pressure forces the extinguishant into the auxiliary power unit shroud, where it suffocates the fire. The indication that the cartridge has fired is given by the displacement of a yellow disc, which is positioned on the side of the aircraft, where it can be checked during the walk-round inspection. The red disc alongside the yellow disc will become displaced if the fire bottle has become too hot or its internal pressure has become too high. There are three basic requirements which must be satisfied before we can start a gas turbine engine. They are that the compressor turbine assembly must be rotated to get air into the combustion chambers, that fuel must be provided in the combustion chambers, that ignition must also be provided in the combustion chambers to start the air-fuel mixture burning. Supplementary to these basic prerequisites for engine starting are two other requirements which satisfy servicing essentials. The necessity to motor over the engine with no igniters operating. This is sometimes called a blowout or motoring over cycle. The necessity to motor over the engine usually only occurs when there's been a failure to start. A failure to start is sometimes called a wet start. The need for the igniters to be operated independent of the start cycle. There are several methods of obtaining engine rotation upon engine start. The most common methods of rotating the high-pressure compressor on modern civil aircraft are the electric starter motor, the air starter motor. Any engine starter system will have a duty cycle. The duty cycle is the maximum time that the starter motor is allowed to be energized. The duty cycle may have to be followed by a cooling down period before the starter motor can be re-energized. The electric starter motor was the original means of starting a gas turbine engine, and is still used in smaller executive jets and helicopters. However, it's fallen out of favour in larger and more modern engines because of its weight. This picture shows a Dart engine where the electric starter motor is fixed in front of the compressor casing. The electric starter motor can, however, be attached to the engine accessory gearbox. In the latter circumstance, the starter drives the compressor through the gearbox. Rapidly becoming more popular on smaller engines is the starter-generator combination, which, because of its dual purpose, has a greater usefulness-to-weight ratio. The air starter motor is possibly the most popular starting system on large gas turbine engines. It's light, simple to use and very economical, insofar as it utilizes low-pressure air as its power source. The air starter motor is attached to the accessory gearbox of the engine. The sources of air available for engine start, in order of preference, are the Aircraft Auxiliary Power Unit, or APU. Use of an APU does not cost the airline anything, so it definitely will be the favourite method of supplying air for engine starting. The Ground Start Unit. If a ground start unit is required, perhaps because of APU unserviceability, the airline will have to pay for its use. This is understandably not too popular with the airlines. A crossbleed start, where air from an already started engine is used. A crossbleed start doesn't cost the airline anything, but it does require that the engine that supplies the air has power applied to it. In the crowded environment of the ramp, applying power to an engine carries obvious risks, and some airport authorities are reluctant to give permission to the pilot to carry out this type of operation. Air from one of these sources is fed through an electrically controlled air start valve to the starter motor's air inlet, where it's used to turn the turbine rotor. The air is subsequently exhausted to atmosphere. The turbine rotor turns the reduction gear, which rotates the engine high-pressure compressor shaft through a ratchet clutch arrangement, which is designed to prevent the starter motor being driven by the engine after engine start. The danger, should this happen, is that the starter motor will rotate at a speed sufficient to cause it to break up due to centrifugal force. A flyweight cutout switch may also be included in the control circuit of the air start valve. This shuts off the starting air supply by de-energizing the air start valve. This device will automatically terminate the engine start cycle when the engine has reached a speed slightly in excess of self-sustaining speed. We'll explain the starting sequence of a generic twin-spool medium bypass gas turbine engine using two methods. Firstly, we'll go through the sequence using the engine controls to demonstrate the required actions, and the engine instruments and a generic air starting supply layout to illustrate the results of those actions. The second method will utilize a graphical representation of the relationship between RPM and EGT during a normal engine start sequence. This very simplified air start supply layout for a twin-engined aircraft shows each engine fitted with an air starter motor. When engine start is selected, each starter motor will be supplied with low-pressure, high-volume air from either the APU, the ground start unit, or another engine which is already running and capable of supplying air. On this particular start, we'll utilize the aircraft's APU to supply air. The aircraft's normal bleed air system ducting is utilized to pass the air to the starter motor. Non-return valves at the low-pressure and high-pressure engine bleed positions prevent air leaking back into the engine compressor during engine start. The engine instruments which require the most attention during the engine start sequence are the exhaust gas temperature gauge, EGT, and the high-pressure compressor rotational speed gauge, N2. These two parameters must be monitored closely to ascertain whether or not the start cycle is proceeding safely. Other instruments that should be monitored during the start are fuel flow, engine oil pressure, low-pressure compressor rotational speed, otherwise known as N1, system duct pressure, and the start valve open light. Normally the number 2 engine will be started first. For the first start of the day, right ignition is selected, and the number 2 engine start switch is selected to ground, which is the ground start position. The selection of ground opens the APU control valve and the number 2 engine air start valve. To indicate that air is getting to the starter motor, the start valve open light above the engine instruments illuminates. The starter motor turns the high-pressure compressor, which we can note by checking the N2 reading. This is an appropriate time to start timing the starter motor duty cycle. As the N2 increases, the oil pumps will produce sufficient pressure to extinguish the low oil pressure caption. At 24% N2, the number 2 engine start lever should be moved to the idle detent. This supplies fuel to the engine and initiates the AC ignition system. The operator should keep his hand on the start lever in case of an engine starting fault, in which case he should immediately close the start lever. On most twin or triple spool engines, it's advisable to ensure that the other spools are rotating in the correct direction, especially if starting engines with a tailwind. A short time after the start lever has been opened, the engine should light up. This is indicated by an increase in the EGT and an increased rate of acceleration of N2. At approximately 46% N2, the start switch will automatically move to the off position, and the start valve open light will extinguish. The starter duty cycle is now complete, and the N2 should continue to increase to the ground idle value of between 58 to 62%. When the engine RPM has stabilized at ground idle, the fuel control and, if appropriate, the ignition switch can be released and the after-start checks carried out. We'll now use this graph, together with the simplified air start supply layout, as the second method of demonstrating how the exhaust gas temperature and high-pressure compressor RPM relate to each other during a normal engine start cycle. As before, we'll again use the APU as the source of starting air. Upon engine start selection, air is fed from the ducting to the starter motor via the air start valve. The compressor accelerates under the influence of the starter motor and starts to force air through the combustion chambers. Initially, fuel and ignition are not supplied. Each type of engine will have a specific high-pressure compressor RPM when both the fuel supply and the ignition should be activated. Fuel and ignition are, in this case, selected by moving the start lever to the idle detent when N1 reaches 24%. Engine light-up is indicated by an increase in exhaust gas temperature and must occur within a specified time. 20 seconds is typical. The initial increase in EGT is quite sharp because of the fact that as combustion does not occur immediately after ignition is selected, there is an initial build-up of fuel in the combustion chamber. Once this fuel does ignite, it tends to overpower the cooling effect of air being fed from the compressor. Once the excess fuel is burnt off, however, and the fuel-air mixture becomes more balanced, the increase in EGT steadies. The gas, which is being produced in the combustion chambers, now adds impetus to the turbine blades, which eases the task of the starter motor, and the engine continues to accelerate. The accelerating engine drives the high-pressure fuel pumps faster and faster, until they eventually manage to drive sufficient fuel through the fuel control unit, which enables it to supply the idle level of fuel flow to the burners. However, the compressor is not yet running at idle RPM, so once again there is too much fuel being supplied to the combustion chambers, and not enough cooling air. Evidence of this is given by the second steep rise in the EGT. Eventually the engine accelerates to self-sustaining speed, which is approximately 36% N2. The starter motor is not, however, deselected at this point. It's kept operating to assist the engine to accelerate a little more. This gives the engine a better chance of reaching idle RPM without exceeding its limiting EGT. The igniters and the air supply to the starter motor will be cancelled automatically by an N2 speed switch at 40% N2. As engine acceleration continues towards this point, the EGT peaks. But as the airflow and the fuel flow become balanced at their idle RPM values, the EGT drops to the value appropriate to idle RPM. Ground idle RPM is approximately 60% N2 and 25% N1. A motoring overcycle, sometimes called a blowout cycle, may be required if there has been an unsuccessful attempt to start, as appears to be the case here. Any fuel which remains in the engine after an unsuccessful attempt to start has to be evaporated, blown out, or allowed to drain away before another attempt can be made to start the engine. Carrying out a blowout cycle should prevent torching, which is a phenomenon caused by excess fuel, which remains in the engine, catching fire in a subsequent attempt to start. To achieve a blowout cycle, the starter motor is activated without the selection of either fuel or the ignition system. When it's used for a blowout cycle, a typical air turbine starter motor has a duty cycle of 2 minutes on, followed by a 5-minute cooling down period. Always check the manual to determine the exact duty cycle of the starter motor that your engine has fitted. In the event of an engine flaming out while the aircraft is airborne, it may only be necessary to initiate the fuel flow and activate the ignition system without operating the starter motor to achieve a relight. The starter motor should not be required to rotate the engine in these circumstances because the engine should already be windmilling. On this aircraft, if both ignition systems are selected and the appropriate engine selector moved to the flight position, a relight should be achieved if the failed engine's start lever is moved to the idle detent. Evidence that an attempt to relight has been successful will be obtained from the EGT and RPM gauges. A rise in the value of either of these shows that a relight has occurred. It's really only possible to determine that a hot start is happening by comparing its indications to those of a normal start. The EGT may initially rise as normal, but then a rapid rise towards the engine's EGT limit, caused by a hot start, will become apparent a few seconds after light-up. In many cases, the only chance of stopping the temperature limit being exceeded lies in having the ability to switch off that engine's fuel supply as quickly as possible. waiting for instructions or discussing the indications will almost certainly cost you or your company the price of a new engine. Hence the advice to keep your hand on the fuel supply control. If the EGT exceeds the limit by only 1 degree, the engine is to be considered unserviceable. The reasons for a hot start lie almost entirely in having either too much fuel or not enough air to cool the gases through the turbine. A surplus of fuel can be caused by a variety of reasons, such as the throttles either not being set to idle during the pre-flight check or being knocked away from the idle position after the pre-flight check. A shortage of sufficient cooling air can be caused by the engine not rotating fast enough, maybe because the duct pressure is too low to drive the starter motor at the required speed. Slow engine rotation could also be caused because ice accretion within the compressor annulus has caused a partial seizure of the compressor. A hot start can also be caused by the aircraft being positioned, perhaps for its second start of the day, with the wind going up the jet pipe, as opposed to the ideal situation when the wind would be going into the intake. The tailwind will make the job of the starter motor more difficult, and it will have more trouble pushing sufficient air through the engine quickly enough to keep the core temperature within limits. The residual heat that remains in the engine after shutdown will exacerbate the problem. The failure of the gas turbine engine to start, more commonly known as the wet start, is indicated by its EGT not rising and its RPM stabilizing at the maximum that the starter motor can achieve. If the engine fails to light up within the required time limit, which is usually about 20 seconds, then the ignition supply should be deselected and the fuel supply shut off. However, it may be some time before it's realized that there is a problem, and that the problem is a wet start. Starting malfunctions on gas turbine engines are rare and always come as a surprise, except in the flight simulator, where they tend to become the norm. Thus, there can be a long period during which fuel is being pumped into the engine before the problem becomes apparent. Throughout that period, the combustion chambers and exhaust system are becoming saturated with fuel. The fact that fuel is entering the engine can be confirmed by a glance at the fuel flow meter indication at the instant of moving the start valve to the idle detent. Two dangers exist if this fuel is ignited. Firstly, it will cause a very large jet of flame to issue from the exhaust system, the phenomenon called torching. And secondly, the rise of EGT may well be uncontrollable and could exceed its limitation. To prevent torching and excessive EGT, before attempting a second start, a motoring over or blowout cycle must be carried out. So, immediately the wet start is diagnosed, do not terminate the start cycle. Instead, promptly shut off the high-pressure fuel supply and deselect ignition, and then allow the starter to continue to turn the compressor for the time remaining in that start cycle before attempting a blowout cycle. These actions will allow the compressor to start blowing out any fuel from the engine even before you carry out the blowout cycle proper. The obvious cause of a gas turbine engine failing to start is a lack of ignition. The ignition units are generally quite reliable. However, they do sometimes fail. It can be difficult to determine from the cockpit of a large airliner whether or not you have sparks in the engine. On some aircraft there is a clue which is given by the very nature of the igniter units themselves. Really high energy outputs will sometimes make themselves heard on the intercom system as a background buzz. If you can hear that noise on the intercom during the start cycle, or when the relight facility is selected, then it's probable that the igniter units are operating. Alternatively, if your starter crew trust you, and if it's safe for them to do so, you could direct them to the rear of the engine and, having selected relight, ask them to listen for the asynchronous ticking noise which two high-energy igniters make when they're feeding sparks to two serviceable igniter plugs. Another cause of a gas turbine engine failing to start could be a lack of fuel, but this is fairly unlikely to occur on an engine that was working perfectly when it was shut down. A check of the fuel flow meter when the start lever is operated will give you ample evidence of whether fuel is being fed to the engine or not. The indications of a hung start are the EGT being higher than would be expected for the RPM at which the engine has stabilized, and the RPM being lower than the engine's self-sustaining speed. The high EGT is, however, usually not greater than the limit. Nevertheless, maintaining the engine in this state will do it no good at all, and could do it a great deal of harm. If a hung start is indicated, then the high-pressure fuel supply must be shut off, and the problem investigated. The usual cause of a hung start is that there is not sufficient airflow through the engine to support efficient combustion. There could be a number of reasons for this insufficient airflow. For instance, if you're at a high-altitude airfield and you're attempting to start an engine which has a contaminated compressor, that compressor will choose this time to make its inefficiency felt. On the other hand, insufficient motive power being applied to the starter motor will prevent it from being able to rotate the compressor fast enough to push the required amount of air through the engine. This means that the gases generated in the combustion chambers will not have sufficient power to assist the starter motor in accelerating the engine beyond self-sustaining speed. Thus, once the starter motor cycle has finished, the engine RPM remains stable below the figure that will enable it to accelerate up to ground idle speed. Engine rundown time, or spool down time, is the time taken for the engine to stop after the high-pressure fuel supply is shut off. When the engines are shut down after flight, a mental note should be taken of the rundown time of each engine, and a comparison made between those times. Any engine with a rundown time appreciably less than the others should be noted. A short rundown time may be indicative of an impending malfunction.
In this lesson, we will examine the properties of the fuel used in aircraft engines. Aircraft piston engines use gasoline and gas turbine engines kerosene. Both of these fuels are produced from crude oil. In simple terms, the required fuel is extracted from the crude oil by a distillation process. The oil is boiled in a furnace, and then the oil vapour is cooled in a distillation column. The various hydrocarbons in the oil all have different boiling points, so they condense out of the vapour and are tapped off at different points in the column. The heavy oils condense out first and are collected near the bottom. The process then continues up through the tower, with kerosene and gasoline, which are relatively light and volatile, being taken out near the top. The specification for an ideal fuel for a gas turbine engine includes the following main requirements. It should flow easily under all operating conditions. It should have complete combustion under all conditions. It needs to have a high calorific value. The calorific value of a fuel is a measure of the amount of heat released during its combustion. It is measured in British thermal units per pound or kilojoules per kilogram. It should be non-corrosive. There should be no damage to the engine from combustion byproducts. The fuel should present a low fire hazard. Engines should start easily, and the fuel must be able to lubricate the moving parts of the fuel pumps and other components in the system. In practice, the cost of satisfying all of these criteria is prohibitive, and therefore compromises have to be made. As we said, gas turbine-engined aircraft use kerosene fuels. These are heavier and less volatile than gasoline fuels. They are placed between gasoline and diesel fuel in the distillation process. The two main types of gas turbine fuel in use in civilian aircraft are aviation turbine fuel, or AVTUR, and aviation turbine gasoline, or AVTAG. In the United Kingdom, the specifications for these fuels are issued by the UK Aviation Fuels Committee on behalf of the Defence Materials Standardisation Committee. There are two grades of AVTUR in use. Jet A1 is used in Europe and most of the rest of the world. while Jet A is used in the United States of America. Jet A1 is a kerosene-type fuel with a nominal specific gravity of 0.8 at 15 degrees Celsius. It has a flash point of 38.7 degrees Celsius and a waxing point of -50 degrees Celsius. Waxing is explained later in the lesson. Jet A is a similar type of fuel to Jet A1, but it has a waxing point of -40 degrees Celsius. Gas turbine fuels are not dyed for identification. They retain their natural colour, which can range between what is termed water clear to a straw yellow. AVTAG is known in civil aviation as Jet B. It is not generally used in civilian aircraft. It is a gasoline and kerosene mix with a nominal specific gravity of 0.77 at 15 degrees Celsius. It has a flash point of -20 degrees and a waxing point of -60 degrees Celsius. Because of the very low waxing point, it may be found in use at a small number of civil airfields in very cold climates. If a fuel sample is placed in a clear glass container and swirled vigorously and the sample appears cloudy or hazy, then there could be one of two reasons for this. If the cloudiness appears to rise quite rapidly towards the top of the sample, then air is present. But if the cloud falls quite slowly towards the bottom of the sample, then water is present in the fuel. Having said that, a cloudy appearance usually indicates the presence of water. A certain amount of water is present in all fuel. The water, which is dissolved in the fuel, gives rise to a number of fuel system problems. As an aircraft climbs to altitude, the fuel is cooled and the amount of dissolved water it can hold is reduced. Water droplets form, and as the temperature is further reduced, the droplets turn into ice crystals which can block fuel system components such as filters. Microbiological fungus called Cladosporium resinae is present in all turbine fuels. This fungus grows rapidly in the presence of water to form long green filaments which can block fuel system components. The waste products of the fungus are corrosive, especially to fuel tank sealing substances. The inclusion of a fuel system icing inhibitor, or FSII, in the fuel will help to overcome these problems. The inhibitor in common use inhibits the ability of the water in the fuel to freeze and acts as a pesticide, which retards the growth of the fungus in the fuel. As we have already said, water is always present in fuel. The amount will vary according to the efficiency of the manufacturer's quality control and the preventative measures taken during storage and transfer. Further measures can be taken to minimize water accretion once the fuel has been transferred to the aircraft tanks. If the fuel can be allowed to settle after replenishment, then the water droplets, being heavier than the fuel, will fall to the bottom of the tank and can then be drained off through the water drain valve, which is situated in the sump in the lowest part of the fuel tank. Once the fuel is in the aircraft fuel tanks, the main source of water contamination is the atmosphere that remains within the tank. If the tanks are topped up to full, then the atmosphere is excluded together with the moisture it contains, thus minimizing the likelihood that the fuel will be contaminated. Caution is required here. Filling up the tanks may prove an embarrassment later if the ambient temperature rises, as the fuel in the tanks will expand and there is the danger that it may spill out of the vent system. Filling the fuel tanks may also incur a performance penalty, as the aircraft may be too heavy to take off with the required passenger or cargo load, and some fuel may have to be removed. As a further precaution, in order to prevent any ice crystals blocking fuel filters and jets, the fuel may be passed through a fuel heater located on the engine, which uses hot air from the engine compressor to remove any ice crystals which may have formed in the fuel when it is cooler than 0 degrees Celsius. Some systems utilize a fuel-cooled oil cooler as well as, or instead of, a fuel heater. The fuel-cooled oil cooler uses the hot engine oil to warm the fuel and in doing so produces the added benefit of cooling the oil. A number of additives may be blended into the fuel either at the refinery or the airfield to improve the operating ability of the fuel. A lubricity agent is added to the fuel to reduce wear in moving parts of the fuel system components. Static dissipator additives partially eliminate the hazards of static electricity generated by the movement of fuel through modern fuel transfer systems. This would otherwise be a particular problem with the high flow rates generated during refueling and defueling. Corrosion inhibitors protect ferrous metals in fuel handling systems, such as pipelines and storage tanks, from corrosion. Certain of these corrosion inhibitors improve the lubricating qualities of some gas turbine fuels. Metal deactivators suppress the tendency, which some metals, particularly copper, have to cause the fuel to oxidize. We are now going to talk about fuel waxing. This is something that happens to the fuel when it is extremely cold. Do not confuse this with the water in the fuel freezing. Gas turbine fuel consists of many hydrocarbons, each with its own freezing point, so it does not become solid at one temperature in the same way that water does. As the temperature of the fuel drops, the heavy hydrocarbons which have the highest freezing point freeze first and form wax crystals. As the temperature drops further, the hydrocarbons with slightly lower freezing points start to solidify. And so on as the temperature continues to fall. The waxing point of a fuel is the temperature at which the wax crystals begin to form. Jet A1 has a waxing point of -50 degrees Celsius, so waxing is only a problem for aircraft operating for prolonged periods at high altitude in very low temperatures. The crystals can clog the fuel filter and interfere with the operation of the engine fuel control unit. The effects of waxing can be minimized by the refinery keeping the heavy hydrocarbons in the fuel to a low level. The temperature at which a liquid boils will reduce as the pressure on its surface reduces. As an aircraft climbs, the pressure on the surface of the fuel reduces, and with that reduction comes an increased likelihood that the fuel will boil and form vapour in the pipelines. The vapour locks that this effect causes can cut off the fuel supply to the engine, with the result that the engine will stop. Fuel booster pumps fitted inside the tanks can help to overcome this problem by pressurizing the fuel in the pipelines from the tank to the engine, pushing fuel towards the engine, rather than engine-driven pumps sucking fuel from the tanks and further reducing the pressure. Specific gravity, or SG, is defined as the ratio of the density of a given solid or liquid substance to the density of water. Or to put it more simply, it is the weight or mass of the liquid divided by the weight or mass of an equal volume of water. So, in the example shown here, we have 1 gallon of fuel in the left container and it weighs 8 pounds. In the right container there is an equal volume, 1 gallon of water, and it weighs 10 pounds. The specific gravity of the fuel then is 8 divided by 10, or 0.8. Specific gravity has no dimensions. The higher the specific gravity of a fuel, the greater will be the mass or weight of fuel for a given volume. And conversely, the lower the specific gravity, the less will be the mass or weight for a given volume. The specific gravity of fuel varies inversely with its temperature, so depending on the storage conditions, the specific gravity of the fuel supplied to an aircraft may be different from the standard value. On modern aircraft fuel systems, this usually makes little difference as fuel in the aircraft's tanks is measured in mass or weight rather than volume, with the fuel quantity measuring system compensating for changes in fuel-specific gravity. However, if a high fuel load is required, it may not be possible to get sufficient volume of fuel on board for the required mass if the specific gravity of the fuel is low. That is the end of the lesson. The tables listing characteristics of the various fuel types are shown on the screen. Remember that ice crystals formed by water in the fuel are prevented from blocking the fuel filter by heating the fuel upstream of the filter using either hot air or oil.
The entire system, which stores, carries and controls the fuel supply for the engines, can be divided into two sections: the airframe fuel system and the engine fuel system. Here we'll look specifically at the engine fuel system, which receives the low-pressure fuel supply from the aircraft fuel tanks, which are part of the airframe fuel system. The engine fuel system increases the fuel pressure to a value that the fuel nozzles in the combustion chamber can use, and then controls the volume of fuel into the engine so that it conforms to the engine's requirements. The engine fuel system consists of a number of components which we'll now describe in more detail. The booster pumps, which are situated in the wing and centre tanks of the airframe fuel system, pass fuel through non-return valves to the engine via the low-pressure fuel cock. The low-pressure fuel cock is electrically operated. It can be shut automatically if the engine fire control handle is activated. If a component of the fuel system needs to be removed, for whatever purposes, the low-pressure fuel cock can be used to shut off the supply of fuel to the engine to facilitate the removal. If the high-pressure fuel cock cannot be used to shut down the engine for whatever reason, as an alternative, the low-pressure fuel cock can be used to stop the engine. However, using the low-pressure fuel cock to shut down the engine instead of the high-pressure fuel cock will mean that the engine will take much longer to shut down. This is because the pipeline between the low-pressure fuel cock and the engine contains a considerable amount of fuel, which will maintain the supply to the burners for some time, whereas in the case of the high-pressure fuel cock, very little fuel is contained in the pipeline between it and the combustion chambers. After it's passed through the low-pressure fuel cock, the fuel then enters the engine fuel system and is delivered to the low-pressure fuel pump. The low-pressure fuel pump is sometimes called the backing pump because it will attempt to back up the fuel supply to the engine in the event of failure of both of the booster pumps in the wing tanks. The low-pressure fuel pump is used to supply positive fuel pressure directly to the high-pressure pump. By maintaining a positive pressure, the low-pressure pump minimizes the chance of cavitation occurring at the inlet of the high-pressure pump. The low-pressure fuel pump is driven by the engine's accessory gearbox, which itself is driven by the high-pressure compressor shaft. A fuel-cooled oil cooler is fitted in the majority of gas turbine engine installations. The oil cooler serves the double purpose of cooling the oil and also heating the fuel. By raising the temperature of the fuel, the oil cooler eliminates the formation of ice crystals, which may block components downstream in the fuel system. The oil feed line to the fuel-cooled oil cooler incorporates a pressure-maintaining valve. This valve keeps the oil pressure in the cooler higher than the fuel pressure. If the oil cooler does develop an internal leak, then the fact that the oil pressure is higher than the fuel pressure will ensure that the oil leaks into the fuel system, rather than the fuel leaking into the oil system, which could be very dangerous. The fuel heater assists in the warming of the fuel, and thus the elimination of ice crystals. The fuel heater, working in conjunction with the fuel-cooled oil cooler, uses compressed bleed air to warm the fuel to automatically maintain a predetermined fuel temperature. The automatic temperature control can be achieved by the action of a Vernotherm thermal actuator. The thermal actuator incorporates a material which is sensitive to temperature change. This is used to open or close a valve which regulates the entry of hot air into the fuel heater from the engine compressor. The low-pressure fuel filter is the first line of defense, protecting the delicate control components within the high-pressure fuel pump and the fuel control unit from the effects of dirt or contamination. The low-pressure filter is usually a replaceable paper filter element, which is capable of filtering out particles larger than 50 to 100 microns. The flow meter measures the instantaneous fuel flow in gallons per hour, kilograms per hour, or pounds per hour. The flow meter may also include an integrating system, which can add the total amount of fuel used. There are basically two types of flow meter in use on large jet aircraft. They are the vane type and the mass flow measuring type. The vane type of fuel flow meter, which is fitted to older aircraft systems, is designed to measure volume of flow. The flow meter consists of a vane which is moved against the force of a restraining spring by the volume of fuel flowing past it. This system is not too accurate. The mass flow type of instrument can be accurate to within plus or minus 1%. Fuel flowing through the instrument rotates both a drum and a spring-mounted impeller, which have magnets fixed to them. Movement of the magnets is sensed by pickup coils, which translate the difference in angular displacement between the magnets into a mass flow rate. The fuel temperature is sensed as the fuel leaves the fuel heater. Fuel temperature is indicated on the flight deck to allow system monitoring. The fuel pressure is sensed as the fuel leaves the low-pressure fuel filter. Fuel low pressure may be indicated by either an LP fuel warning light or the activation of warnings on the ICAS or ECAM, depending on aircraft type. The high-pressure fuel pump is fitted to and driven by the engine accessory gearbox. The engine accessory gearbox itself is driven by the high-pressure compressor shaft. The high-pressure fuel pump illustrated is representative of one type of pump employed. It's a plunger-type pump. It can be used as a single unit if the volume of fuel required is not too great, but in larger engines 2 units can be driven together to supply a greater fuel flow. Several plungers are fitted on a rotor assembly. The plungers are rotated against a stationary cam plate, which causes them to reciprocate within the bores that contain them on the rotor assembly. The distance that the plungers move during this reciprocating action is dictated by the angle of inclination of the cam plate. Here we see the cam plate angled so that the plungers stay in the same position in their bores as the rotor drives them round. Now the cam plate angle is such that the springs force the plungers to their maximum stroke when they are at the top of the cam plate, sucking fuel into the bores. And the cam plate forces the plungers to their minimum stroke when they are at the bottom of the cam plate, forcing fuel under pressure to the outlet of the pump. The angle of inclination of the cam plate is controlled by a servo piston, which itself is controlled from the fuel control unit. Most fuel systems incorporate a fuel filter into the output of the high-pressure fuel pump to prevent very fine particles entering the extremely small passageways inside the fuel control unit. The fuel filter is composed of a number of wire mesh screen discs. The spur gear type fuel pump is simpler and lighter in construction than the plunger type fuel pump, and like the plunger type pump, the spur gear type pump is driven by the accessory gearbox. The output of the spur gear type pump is directly proportional to its rotational speed. The fuel control unit controls the fuel flow to the burners for every thrust setting. There are 2 types of hydromechanical fuel control systems still used on gas turbine engines. They are the pressure control system and the proportional flow control system. The proportional flow control system is the more popular of the 2 types because it is more compact than the pressure control system, and it's not sensitive to the effect of flow variations that occur downstream of the throttle. The proportional flow control system is the type we'll use to describe the individual parts of a fuel control unit. Various devices within the fuel control unit are used to adjust the fuel flow to cater for variations in air intake pressure, engine acceleration control, exhaust gas temperature, RPM limiting, and compressor delivery pressure. Variations in air intake, or P1 pressure, require that the fuel flow to the burners is adjusted so that a fixed RPM is maintained for a selected throttle position at all altitudes and airspeeds. This is achieved by the expansion or contraction of a capsule influenced by P1 pressure, which in turn modifies the fuel flow to suit the new conditions. This capsule, known as the barometric pressure capsule, is incorporated in an altitude sensing unit within the fuel control unit. It's necessary to increase the fuel flow to the engine to make it accelerate. However, too rapid an increase of fuel flow into the engine can cause compressor stall and surge. To regulate the fuel flow under conditions of engine acceleration, an acceleration control unit is fitted within the fuel control unit. The acceleration control unit receives information regarding engine intake pressure, P1, and compressor delivery pressure, P3 for a two-spool engine, and uses this information to adjust a fuel metering plunger. The fuel metering plunger effectively acts as a second throttle valve in series with the main throttle, and it regulates the fuel flow to achieve the fastest engine acceleration without causing stall or surge. Exhaust gas temperature is probably the most important parameter in a gas turbine engine. To obtain maximum efficiency, the engine must be run at the highest possible temperature in the turbine without melting the materials from which it's made. To achieve these conditions and yet still allow the engine to be a practical, user-friendly unit, automatic monitoring of the exhaust gas temperature is combined with a top temperature control unit. The top temperature control facility allows the pilot to select full power at any time without risking a meltdown in the turbine assembly. Thermocouple probes are positioned in the gas stream, either within the turbine assembly or close after it. The output of these thermocouples is used to measure the temperature at the rear of the engine. This output is passed both to the cockpit instrumentation and to a temperature control signal amplifier. The electrical output of this amplifier drives a solenoid which indirectly controls the fuel flow to the engine. The ability of the compressor to withstand internal pressure is limited by the strength of the materials from which its casing is made. If the compressor casing is subjected to pressures greater than its design maximum, it will break, with probably catastrophic consequences. To prevent compressor casing failure, the fuel control unit incorporates a power limiter device. The power limiter receives signals of both intake pressure, P1, and compressor delivery pressure, P3. The ratio of P3 pressure to P1 pressure can be found by combining these signals. A system of capsules and levers controls the fuel flow to the engine so that a maximum pressure ratio is never exceeded, and thus the integrity of the compressor casing is retained. If excessive centrifugal force is to be prevented from destroying the compressor spools, their maximum rotational speeds must be limited. There are basically two methods of achieving this compressor rotational speed limitation. The first method of controlling the rotational speed of a compressor, usually the low-pressure compressor, depends on an electrical signal proportional to the speed of the compressor shaft. A tachogenerator, or electronic speed sensor, which is driven by the appropriate shaft, sends signals to an amplifier. If the output of the tachogenerator approaches a predetermined maximum level, the fuel flow will be adjusted to prevent the maximum RPM being exceeded. The second method of controlling the rotational speed of a compressor is normally used to control the speed of rotation of the high-pressure compressor shaft. This high-pressure compressor shaft drives the accessory gearbox, which in turn drives, among other things, the high-pressure fuel pumps. Fitted within the high-pressure fuel pump is a hydromechanical governor. The hydromechanical governor uses hydraulic pressure as its controlling parameter. The hydraulic pressure, which is generated inside the pump by the rotation of the moving parts, is proportional to engine speed. As engine speed, and thus hydraulic pressure, builds, it acts on a diaphragm. Movement of the diaphragm opens valves which bleed off some of the servo piston pressure, which reduces the high-pressure fuel pump cam plate angle. This reduces the high-pressure fuel pump output and attenuates the fuel flow to the burners. The high-pressure fuel cock, sometimes called the high-pressure fuel shutoff valve, controls the flow of fuel between the fuel control unit and the fuel spray nozzles in the combustion chambers. The high-pressure fuel cock is the control normally used for starting or stopping the fuel supply to the engine. The high-pressure fuel supply may be mechanically controlled by a lever on the flight deck, or it can be electrically controlled by an actuator, which is also controlled by a switch on the flight deck. When the engine is shut down, any fuel remaining in the fuel manifold would tend to boil as a result of residual engine heat. solid deposits resulting from the boiling will clog the fuel lines into the system, which would be detrimental to the operation of the engine. The dual inlet line fuel spray nozzle system can utilize a pressurizing and dump valve to prevent this happening. When the engine is shut down, fuel pressure generated by the opening of the high-pressure fuel cock, which was holding the dump valve closed, is lost. The spring inside the dump valve will now be able to open the valve and allow the contents of the fuel manifold to pass back to the supply line. At the same time, the inlet check valve will close, maintaining fuel inside the unit ready for the next start. When the high-pressure fuel cock is opened, a signal of fuel pressure is sent to the dump valve, which moves over and shuts off the fuel flow back to the supply line. In moving over, the valve also opens the passageway to the primary manifold. Fuel pressure from the fuel control unit will open the inlet check valve and pass through the filter to the primary fuel manifold. At a predetermined engine speed, the fuel pressure from the fuel control unit will build sufficiently to open the pressurizing valve, and fuel will also begin to flow into the main manifold, expanding the fuel spray pattern and assisting in better atomization. Many modern gas turbine engine installations utilize electronic engine control to enable better fuel economy, better reliability, and prolonged engine life. Two types of electronic engine control are currently in use: the supervisory engine control system, the full authority digital engine control system. The supervisory engine control system uses a computer which receives inputs of various engine operating parameters and controls a standard hydromechanical fuel control unit. The fuel control unit responds to the electronic engine control commands and performs the functions necessary for engine operation and protection. The computer will monitor EPA, throttle lever angle, Mach number, engine intake pressure and temperature, and will maintain a constant thrust regardless of changes in air pressure, temperature or flight environment. Any fault with the electronic engine control will cause the system to revert to manual control. The full authority digital engine control system, commonly called by its initial letters FADEC, receives all the necessary data for engine operation and takes over virtually all of the steady state and transient control functions, which includes compressor airflow control. The hydromechanical fuel control unit is now redundant, except for the throttle valve and fuel shutoff cock, which reduces the mechanical complexity of the engine fuel system. The FADEC system will monitor all of the normal engine parameters and prevent limitations being exceeded while controlling the engine through all modes of operation, for example starting, idle, acceleration and deceleration, takeoff, climb and cruise. In other words, it controls the engine in response to the throttle lever position or the flight management computer thrust demand. The digital computer which is required to run the system has to be considered an essential component of the engine, just as essential as the compressor or the turbine. This is because a complete failure of the FADEC system would cause the complete loss of the engine thrust. To minimize the chances of a single failure causing the loss of an engine, the FADEC system incorporates two separate identical digital channels. Each channel is able to provide information to enable all engine functions. The FADEC system can be powered from the aircraft electrical system, but in most modern aircraft the system is driven by a separate generator fitted to the accessory gearbox of the related engine. This concludes the lesson on engine fuel systems.
Air is taken or bled from the compressor of a gas turbine engine to be used for a number of purposes. This heated pressurized air, which is known as bleed air, is used internally within the engine for cooling and sealing. It is also used externally to the engine to service many aircraft systems in a number of different ways. In this lesson, we will examine how bleed air is extracted from the engine and the effect this has on engine performance. We will also look at which aircraft systems use this air. For use outside the engine, air is typically bled from two sources. We will use this simplified diagram to show them. The first source is an outlet on an early stage of the compressor which supplies a continual low-pressure bleed. This continual low-pressure bleed, when system demand requires, is supplemented by a second source of air taken from a higher pressure part of the compressor through an automatically operated control component called the high-pressure bleed valve. During high engine power operations, the low-pressure bleed is usually of sufficient pressure to meet all demands, and the high-pressure bleed valve will be closed, shutting off the high-pressure air supply. During low engine power operations, the low-pressure bleed pressure will fall and the high-pressure bleed valve will open to ensure both an adequate pressure and sufficient airflow. The high-pressure air is prevented from flowing back into the compressor through the low-pressure pipe by a non-return valve. All of the bleed air supply from the engine can be shut off, if required, by the operation of a bleed air isolation valve. The position of the isolation valve is controlled by a switch on the flight deck. The isolation valve will automatically close when the engine fire handle is operated to isolate that engine bleed air from the rest of the aircraft. In some systems, fan outlet or bypass air is used in a pre-cooler. The pre-cooler uses the fan air to cool the bleed air in a cooling matrix, thus controlling the temperature of the bleed air going into the system. The fan air can also be used for cooling the engine oil and the electrical generator constant speed drive unit. Shown here is the bleed air system from a typical two-engined aircraft. The only component that we have not discussed is the cross-bleed isolation valve. This valve can be opened to allow one engine to supply all of the services in the event of a failure of the other engine. On the ground with the engine stopped, bleed air can be supplied from the auxiliary power unit or from a ground air cart. When air is bled from the compressor, it reduces the air mass flow through the engine, which has a detrimental effect on the thrust of the engine. Here we show how the instruments will look with the left engine supplying bleed air and the right one not. There will be a reduction in the amount of thrust being produced by the engine. This will be reflected on the engine pressure ratio gauge. The specific fuel consumption of the engine will therefore increase whenever an engine bleed is opened. Reducing the mass flow through the engine also has the effect of reducing the amount of air apportioned to the cooling of the combustion chamber. This will have the effect of increasing the exhaust gas temperature. Bleeding air from the compressor reduces the load on the turbine. This will have the effect of increasing engine RPM for a given fuel flow. Air bled from the engine compressor is used to service a number of aircraft systems. In the modern turbofan aircraft, these may include air conditioning and pressurization, hydraulic reservoir pressurization, domestic water tank pressurization, thrust reverser actuation, fuel heating, and engine and airframe anti-icing. The use of bleed air in these systems is fully covered in the relevant lessons. However, there are a couple of points that need to be made about how the bleed air system is operated in order to ensure satisfactory operation of the user systems. The bleed air used to supply the air conditioning system is controlled by pack flow control valves, sometimes called pack valves. The pack valves control the flow of air to air conditioning packs. The pack valves enable the pilot to selectively control the air conditioning system and, in the event of a malfunction, particularly one involving smoke in the cabin, shut off the bleed air supply to individual air conditioning packs. During ground de-icing operations, toxic fumes may enter the bleed air system. Bleed air from the main engines and the auxiliary power unit should be closed off during these operations to prevent these toxic fumes from entering the cabin through the air conditioning system. In many systems, the high-pressure bleed valve is scheduled to open when airframe anti-icing is selected on. In this situation, the requirement is for lots of hot air. As you know from earlier lessons, by using air from a higher pressure part of the compressor, its temperature will also be higher. That is the end of the lesson. Here is a summary of the main points that you need to take from it. Air is taken or bled from the compressor of a gas turbine engine to be used for a number of purposes. This heated, pressurized air is known as bleed air. An early stage of the compressor supplies a continual low-pressure bleed. When system demand requires, this is supplemented by air taken from a high-pressure compressor stage. The bleed air can be shut off by the operation of an isolation valve, which is controlled by a switch on the flight deck. This valve closes when the engine fire handle is operated. Fan outlet or bypass air may be used in a pre-cooler. When air is bled from the compressor, it reduces the thrust of the engine. This will be reflected as a reduction on the engine pressure ratio gauge. The specific fuel consumption of the engine will increase. The exhaust gas temperature will increase. Engine RPM will increase. Bleed air may be used for the following purposes: air conditioning and pressurization, hydraulic reservoir pressurization, domestic water tank pressurization, thrust reverser actuation, fuel heating and anti-icing. Pack valves enable the pilot to shut off individual air conditioning packs. Bleed air from the engines and the auxiliary power unit should be closed during any ground de-icing operation to prevent toxic fumes entering the cabin. The high-pressure bleed valve may open automatically when airframe anti-icing is selected on. Air is taken or bled from the compressor of a gas turbine engine to be used for a number of purposes. This heated, pressurized air, which is known as bleed air, is used internally within the engine for cooling and sealing. It is also used externally to the engine to service many aircraft systems in a number of ways. In this lesson, we will look at how compressor air is used internally within the engine for cooling and sealing purposes. The main parts of the engine that require cooling are the combustion chamber and the turbine section. We have already discussed combustion chamber cooling in a previous lesson. Here we will examine the cooling of the turbine section. We know from the introduction lesson that the gas turbine engine is a heat engine. High thermal efficiency is dependent upon high turbine entry temperatures. We stated in an earlier lesson that there is a limit to the amount of heat which can be released into the turbine from combustion. This limit is imposed by the materials from which the turbine blades and nozzle guide vanes are manufactured. If turbine blades and nozzle guide vanes are continuously cooled, then the temperature of their operating environment can exceed the melting point of the material from which they are made. In the manufacture of early gas turbine engines, it was considered sufficient to pass low-pressure compressor air through the turbine blades in order to cool them. This is called single-pass internal cooling. The use of single-pass internal cooling retained the temperature of the turbine blades below the critical level at which excessive creep would occur. Creep, you will recall, is the stretching of the material of the turbine blade beyond its ability to reform to its original length. The requirement for greater engine power and efficiency means that higher gas temperatures are necessary in the turbine. Low-pressure compressor air is unable to provide the required amount of cooling on its own. A supplementary source of cooling is required. By passing high-pressure compressor air as well as the low-pressure air through the turbine blades, a reasonable increase in the gas temperature can be accepted before blade failure is experienced. This method of cooling the blades is called multi-feed. A further increase in turbine gas temperature can be tolerated by passing air through small holes in the leading and trailing edge of the blade. This is known as film cooling. Film cooling creates a cooling boundary layer of air around the blade. This boundary layer protects the turbine blade from the onslaught of the hot gases coming from the combustion chamber. It has been found that by passing the air through the turbine blade more than once, the temperature of the blade can be lowered even further. The optimum number of times the air can be passed through the blade has been found to be 5, and quintuple pass multi-feed internal cooling with extensive film cooling is presently considered to be the state-of-the-art in turbine blade cooling. The nozzle guide vanes use a similar method of cooling to that which is used to cool the turbine blades. The one major difference is that only high-pressure compressor air is used. This diagram shows a nozzle guide vane which is cooled by air from the high-pressure compressor using internal cooling and external film cooling. The turbine discs are also heated by conduction from the turbine blades, thus they must be cooled if their disintegration from the effect of continued thermal stress is to be avoided. This diagram shows how the front and rear faces of each of the turbine discs are cooled by high-pressure compressor air. The actual pressure in each disc cavity is controlled by the interstage labyrinth seals. Interstage labyrinth seals are used to control the movement of air between sections of the engine which are operating at different pressures. The seal consists of a number of annular fins over which the air flows. During operation, there is a pressure drop across each fin. The amount of pressure dropped across the seal depends upon the number of fins over which the air must pass. To create two adjacent zones in the engine, one at a higher pressure than the other, we use an interstage seal which has fewer fins in the access to the high pressure zone than are used in the access to the lower pressure zone. More pressure will be dropped by the air passing over the 4 fins before the low pressure zone than will be dropped over the 2 fins preceding the high pressure zone. Some modern turbofan engines use air from the compressor to control turbine blade tip clearance. This system, which is shown here, is called active clearance control. A tubular shroud is fitted closely around the turbine casing. Compressor bleed air is fed through the shroud to control the temperature of the turbine case, preventing it expanding away from close proximity with the turbine blade tips. To prevent the leakage of oil or air into spaces from where it should preferably be excluded, several different types of seal are in current use. Most of these seals are of the labyrinth type. The labyrinth seal consists of fins, which rotate within an annulus of a soft abradable material or a honeycomb structure. Initial running of the engine makes the fins rub against the annulus material, cutting into it to give the minimum clearance. When the labyrinth seal is used to seal bearing chambers, bleed air is fed to the outer side of the seal. The air pressure prevents oil leakage by flowing across the fins from the outside of the seal to the inside. This has the additional beneficial effect of inducing a positive pressure which assists the oil return to scavenge. Where seals have to be placed between 2 rotating shafts, it would be possible, if abradable material was used in the manufacture of the seals, that there would be friction between the fins and the abradable material due to flexing of the shafts. This would create high temperatures and the possibility of shaft failure. An intershaft hydraulic seal, like the one shown here, can be used to provide the seal without risking the sort of problem just mentioned. In this type of seal, the fin, or fins, rotate within an annulus of oil, which is held in place by centrifugal force and prevented from leaking out by air pressure. Any deflection of the shaft will cause the fin or fins to move within the oil, and the seal will be maintained without generating any undue friction or heat. To maintain the efficiency of the engine as high as possible, the air required to perform the cooling and sealing functions is taken from as early a stage as possible in the compressor. In the particular case of the air used to seal bearing chambers, the air is taken from the intermediate stages of the compressor through air transfer ports in the compressor rotor drum and passed through communicating passages to where it is required. The efficiency of a labyrinth seal depends basically upon two factors. Firstly, the mechanical design of the seal, and secondly, the pressure of the sealing air. Oil loss from a serviceable engine working at high power settings and therefore with high compressor pressures is almost negligible. It is during periods of low engine power and thus low compressor air pressures, for instance during the use of idle power during descent from high altitudes, that the greatest oil loss from a serviceable engine is suffered. When cooling and sealing has been carried out, the air which has been doing the job has to be disposed of. This diagram shows that the high-pressure air used for cooling is ejected into the exhaust stream, thus achieving a small performance recovery. The low-pressure air, on the other hand, is fed out through its own dedicated vent pipe. On some engines, the temperature of the air exiting through this vent pipe is monitored to give an indication of the integrity of the engine's internal construction. Any failure which causes the temperature of this air to exceed a predetermined maximum triggers a warning via a temperature sensor. The warning usually consists of a red warning light with the caption IEOH, which stands for Internal Engine Overheat. The response to the warning is a mandatory engine shutdown. That is the end of the lesson on cooling and sealing. Here is a summary of the key points that you should take from it. In order to allow higher exhaust gas temperatures, the turbine blades are cooled by both low pressure and high pressure bleed air. For the same reason, the nozzle guide vanes and the turbine discs are cooled by high pressure bleed air. Some modern turbofan engines use air from the compressor to control turbine blade tip clearance. This system is called active clearance control. Labyrinth seals are used to prevent the leakage of oil or air into spaces from where it should preferably be excluded. The efficiency of a labyrinth seal depends upon the mechanical design of the seal and the pressure of the sealing air. The temperature of the low pressure air exiting through its vent pipe may be monitored to give an indication of the integrity of the engine's internal construction.